The night sky has always called to us. As we gaze upward on a clear evening, away from city lights, we can see it. A soft, milky band of light stretching across the heavens. Our ancestors named it the Milky Way, not knowing they were looking at the edge of our cosmic home, seen from within. Tonight, we embark on a journey through time and space to understand how this magnificent spiral of stars came to be. Our galaxy has a story, a long and quiet one that spans almost 14 billion years. Imagine for a moment the universe before there was a galaxy, before there were stars. There was only darkness then, a vast ocean of hydrogen and helium drifting through the void. But slowly, from that quiet darkness, came the first whispers of light. The story of our galaxy is also our story. Every atom in your body was forged in the heart of a star that lived and died within the Milky Way. The iron in your blood, the calcium in your bones, the carbon that forms the basis of life itself, all were created in stellar furnaces that dotted our galaxy long before our sun began to shine. As we drift through the cosmos on our small blue world, we are not separate from this grand spiral, but part of it, connected to it. The Milky Way is not just something we observe from a distance, it is where we live. It is home. When we look up at the night sky, what we see is only a fragment of our galaxy. The Milky Way stretches over 100,000 light-years from edge to edge, a vast island of stars, so enormous that light itself takes a millennium to cross even a small portion of it. Within this cosmic metropolis, 400 billion stars shine, each a sun unto itself, many with planets of their own circling in endless orbits. Yet for all its vastness, the Milky Way moves with a strange and silent grace. It rotates slowly, taking 230 million years to complete a single turn. Since the time of the dinosaurs, our solar system has traveled only a third of the way around the galaxy. A cosmic year, measured not in days or months, but in eons. The Milky Way was not always as we see it now. Like all things in the universe, it has grown and changed. In its youth, it was smaller, more chaotic, filled with the brilliant blue light of newly formed stars. As it aged, it grew larger, consuming smaller galaxies, developing the elegant spiral arms we see today. And in the fullness of time, it will change again, merging with our neighboring galaxy Andromeda to form something new. But tonight, we look not to the future, but to the past. To understand how our galaxy came to be, we must travel back through time, to the earliest moments after the birth of the universe itself, before the first stars ignited, before the first galaxies formed, before there was anything but darkness and potential. In that ancient time, the universe was not cold and dark as we might imagine, but hot and bright, a sea of energy so intense that not even atoms could form. As this cosmic furnace expanded and cooled, the first elements appeared. Hydrogen, the simplest element, formed first, followed by helium. These primordial gases would one day fuel the first stars, but for now, they simply drifted, gathering slowly under the subtle influence of gravity. The newborn universe was remarkably smooth, but not perfectly so. Tiny variations in density, quantum fluctuations magnified by cosmic inflation, created areas where matter was slightly more concentrated. These subtle differences were the seeds from which all structure in the universe would grow, the places where galaxies would one day form. For hundreds of thousands of years, the universe remained opaque, filled with a fog of electrons that scattered light in all directions. But as temperatures continued to fall, electrons and protons combined to form neutral hydrogen atoms. Suddenly, light could travel freely. The universe became transparent. This moment, known as recombination, gave birth to the cosmic microwave background, the oldest light we can still detect today, the afterglow of creation itself. Then came a period astronomers call the cosmic dark ages. For millions of years, no stars shone in the heavens. The universe was a vast ocean of hydrogen and helium gas, slowly becoming more clumped and concentrated by gravity. In the densest regions, the conditions for the very first stars were gradually taking shape. Before there was a Milky Way, before there were planets or life, there was only this, a universe of possibility, pregnant with potential, waiting for the first spark of light to illuminate the darkness. Before there was a galaxy, there was only darkness. Then from the quiet came light. Over billions of years, a great spiral of stars would form. This is the story of the Milky Way, the galaxy we call home. In the beginning, there was nothing as we would recognize it today. No stars, no galaxies, no planets, not even the empty space between them. The universe was compressed into a point of unimaginable density and heat, a singularity containing all matter and energy that would ever exist. Then, approximately 13.8 billion years ago, this singularity expanded. This moment, which we call the Big Bang, was not an explosion in space, but an expansion of space itself. In less than a trillionth of a second, the universe underwent a period of cosmic inflation, expanding faster than the speed of light. As the universe expanded, it cooled. Within the first 3 minutes, the fundamental forces of nature that govern our world today separated from one another. Gravity, the weakest but most far-reaching of these forces, became distinct. It would later become the architect of galaxies, the force that would bring stars together and shape the Milky Way. In this primordial universe, energy began to condense into matter. The simplest elements formed first. Hydrogen, with just 1 proton and 1 electron, was the most abundant. Helium, with 2 protons, 2 neutrons, and 2 electrons, formed next. Together, these 2 elements would make up more than 99% of all visible matter in the early universe, a composition that remains largely unchanged to this day. For the first 380,000 years, the universe remained an opaque soup of charged particles. Photons, the particles of light, could not travel far before being scattered by free electrons. The universe was a glowing, impenetrable fog. But as it continued to expand and cool, a crucial threshold was crossed. The temperature fell low enough for electrons to be captured by protons, forming stable hydrogen atoms. Suddenly, light could travel freely across the cosmos. This moment of recombination, as it is called, created the cosmic microwave background radiation, a faint glow that still permeates the universe today. This ancient light carries the imprint of the universe as it was just after it became transparent, showing tiny temperature fluctuations that would later grow into the large-scale structures we see today. After recombination came the cosmic dark ages. For millions of years, perhaps hundreds of millions, the universe was filled with neutral hydrogen and helium gas, slowly cooling and becoming more concentrated in some regions due to gravity. There were no sources of light. No stars had yet been born to illuminate the darkness. The universe was quiet, patient, waiting. In this darkness, the seeds of future galaxies were already present. Those tiny quantum fluctuations, born in the first fraction of a second after the Big Bang and preserved in the cosmic microwave background, had created regions of slightly higher density. These overdense regions had a stronger gravitational pull than their surroundings. Slowly, inexorably, they began to draw in more matter. As gravity pulled matter together, these overdense regions grew even denser. The process fed itself, with denser regions exerting stronger gravitational forces, attracting more matter, becoming even denser. This process, called gravitational instability, was the first step toward the formation of all structure in the universe. On the largest scales, matter in the universe is not distributed evenly, but forms a cosmic web. Vast filaments of dark matter and gas stretch across the cosmos, intersecting at dense nodes. These nodes would become the birthplaces of galaxy clusters. The filaments themselves would channel gas toward these nodes, fueling the growth of the first galaxies. But we are getting ahead of our story. Before there were galaxies, there had to be stars. As the Dark Ages continued, the overdense regions of hydrogen and helium gas grew more and more compact. Within these regions, gas clouds became increasingly dense and began to fragment into smaller clumps. When the density and temperature at the center of these clumps reached a critical threshold, a momentous event occurred. Hydrogen atoms began to fuse together, releasing energy in the process. The first stars were born. These first stars, which astronomers call population 3 stars, were unlike any stars that exist today. They formed from pristine gas, containing only hydrogen and helium, with no trace of heavier elements. Without these heavier elements to help radiate away heat, the gas clouds had to become incredibly massive before they could collapse and ignite fusion. As a result, the first stars were giants, perhaps hundreds of times more massive than our Sun. These behemoths burned hot and bright, their intense radiation beginning to ionize the neutral hydrogen around them, creating bubbles of ionized gas in the cosmic darkness. Their lifespans were brief by cosmic standards, perhaps only a few million years. But in their deaths, they seeded the cosmos with the first heavy elements. The cores of these massive stars fused hydrogen into helium, helium into carbon, and continued the process up through the periodic table to iron. Elements heavier than iron were created in the cataclysmic supernovae that ended their lives. These explosions scattered the newly forged elements into space, enriching the gas from which future stars would form. This cosmic enrichment was the first step in a long process that would eventually make life possible. The carbon in your cells, the oxygen you breathe, the calcium in your bones, all were created in the hearts of stars and dispersed in their explosive deaths. We are, quite literally, made of stardust. As the first stars died, they left behind the first stellar remnants. Some collapsed into neutron stars, objects so dense that a teaspoon of their material would weigh billions of tons on Earth. Others, the most massive, collapsed even further, becoming the first black holes. These stellar black holes were small compared to the supermassive black holes that would later form at the centers of galaxies, but they were the first of their kind. With the death of the first stars, the cosmic dark ages began to end. A new era, known as the Epoch of Reionization, had begun. The intense ultraviolet radiation from the first stars and the quasars, powered by the first black holes, began to strip electrons from hydrogen atoms throughout the universe, once again turning neutral hydrogen into a plasma of protons and electrons. But unlike the plasma of the early universe, this ionized gas was now transparent to most wavelengths of light. As more and more stars formed and died, the gas between them became increasingly enriched with heavier elements. This changed the way stars formed. Gas clouds containing these heavier elements could cool more efficiently, allowing smaller clumps to collapse and form less massive stars. The second generation of stars, called Population 2 stars, was born. These Population 2 stars were still poor in heavy elements compared to the stars we see today, but they contained enough to alter their properties significantly. They could be smaller, cooler, and longer lived than their Population 3 predecessors. Some Population 2 stars formed early enough in the universe's history that they are still shining today. Ancient red dwarfs that have been burning hydrogen slowly and steadily for more than 13 billion years. While all of this was happening, dark matter, invisible and mysterious, was also shaping the developing universe. Dark matter interacts with normal matter only through gravity, but it makes up about 85% of all matter in the universe. Its gravitational influence was crucial in drawing together the gas that would form stars and galaxies. Dark matter had begun to clump together even before the universe became transparent, unimpeded by the pressure of radiation that affected normal matter. By the time the first stars were forming, dark matter had already created a complex network of halos, filaments, and voids, a skeleton upon which the visible universe would grow. The largest dark matter halos, with masses equivalent to millions or billions of suns, became the cradles of the first galaxies. Gas fell into these halos, cooled and condensed, triggering waves of star formation. The first protogalaxies were born. These protogalaxies were small and irregular compared to the majestic spirals and ellipticals we see today. They were chaotic places, their shapes constantly changing as they formed new stars, underwent mergers with other protogalaxies, and were buffeted by the explosive deaths of massive stars within them. Among these early protogalaxies were the seeds of what would one day become the Milky Way. About 13.6 billion years ago, in a region of space that had a slightly higher concentration of dark matter than its surroundings, the earliest ancestor of our galaxy began to take shape. This proto-Milky Way was just one of countless similar structures forming throughout the universe at this time. What would make it special was not its origin, which was common enough, but its subsequent history, the unique series of mergers and accretions that would shape it into the galaxy we call home. The early universe was a place of extremes. The first stars were giants that lived fast and died young in spectacular explosions. The first black holes devoured surrounding gas so rapidly that they shone as quasars. some of the brightest objects in the universe. The first galaxies were small but turbulent, forming stars at rates that would be considered starburst events in the modern universe. Yet for all this activity, much of the universe remained empty. The cosmic web of dark matter had created a pattern of filaments and voids, and galaxies formed primarily along the filaments, leaving the voids largely devoid of visible matter. This pattern, established in the universe's youth, persists to this day in the large-scale structure of the cosmos. As we look back to these earliest times, we are looking at the universe as it was before the Milky Way truly existed, when the raw materials from which it would form were still being created and gathered. The stage was being set for the great drama of galactic evolution that would unfold over billions of years. The transition from this early epoch to the formation of recognizable galaxies was gradual. There was no moment when we could say, now the Milky Way exists. Rather, what would become our galaxy grew and changed, absorbing smaller structures, forming and reforming its components, evolving from a formless cloud of gas and newly formed stars into something with structure and pattern. From our vantage point 13.8 billion years after the Big Bang, we look back and try to reconstruct this history. We search for the oldest stars in our galaxy, mapping their positions and calculating their ages. We analyze the motion of stars and gas, looking for patterns that reveal past interactions and mergers. We compare our galaxy to others at different stages of evolution, trying to piece together a coherent narrative from snapshots frozen in time. What emerges from these studies is a portrait of the Milky Way as a dynamic, ever-changing system. A galaxy is not a static object, but a process, a continuous flow of matter and energy, of birth and death and rebirth. The Milky Way we see today is just the current frame in a cosmic film that has been running for almost the entire history of the universe. As the universe aged from hundreds of millions to billions of years old, the first structures recognizable as galaxies emerged from the cosmic fog. These early galaxies were the building blocks from which larger structures would form, the ancestors of the great galaxies we see today. Among them, still in its infancy, was the system that would grow to become the Milky Way. The canvas was blank, but gravity had already begun to paint. The universe remained dark for nearly 100 million years after the Big Bang. During this cosmic night, hydrogen and helium gas continued to gather in the gravitational wells created by dark matter. These invisible halos pulled in more and more gas until the pressure and temperature at their centers began to rise. In the densest regions, something remarkable was about to happen. When the temperature reached approximately 10 million degrees Celsius, at the core of these dense gas clouds, hydrogen nuclei began to move fast enough to overcome their mutual repulsion. They collided and fused together, releasing energy in the form of gamma rays. This process of nuclear fusion is what powers all stars, from those first primordial giants to our own sun today. The first fusion reaction in the history of the universe marked a profound turning point. For the first time since the Big Bang itself, a new source of energy had emerged. Light once again filled the darkness. The first star was born. These first stars were unlike any that exist in our galaxy today. Astronomers call them population 3 stars, the first generation to form in the universe, because they condensed from gas clouds containing only hydrogen and helium, with virtually no heavier elements. Their formation and evolution followed a different path than modern stars. Without carbon, oxygen, and other heavy elements to help radiate away heat, these primordial gas clouds had to grow enormously massive before they could begin to collapse. When they finally did, they formed stars of extraordinary size, perhaps 100 to 300 times more massive than our Sun. These giants blazed with a hot blue light, emitting mostly ultraviolet radiation invisible to human eyes. Their immense mass meant they burned through their hydrogen fuel at a prodigious rate. While a star like our Sun will shine steadily for about 10 billion years, these first stellar giants may have lived for only 2 or 3 million years, a mere eye blink in cosmic time. But in that brief lifespan, they transformed the universe around them. The intense ultraviolet radiation from population 3 stars began to ionize the neutral hydrogen in their vicinity, creating expanding bubbles of ionized gas. This was the beginning of the epoch of reionization, when the universe gradually transitioned from being filled with neutral hydrogen to being filled with ionized hydrogen, as it had been in its earliest moments before recombination. But the greater impact of these first stars came at the end of their brief lives. Having exhausted their hydrogen fuel, they began to fuse helium and then progressively heavier elements in a series of nuclear reactions. This continued until their cores filled with iron, an element whose fusion consumes rather than releases energy. With their energy source exhausted, these massive stars reached a crisis point. Their outer layers collapsed inward at tremendous speed, then rebounded off their dense iron cores in cataclysmic explosions called supernovae. For a brief moment, a single dying star could outshine an entire galaxy. These first supernovae were more than just spectacular cosmic light shows. They were the universe's first factories for elements heavier than helium. In the extreme temperatures and pressures of the explosion, nuclear reactions forged carbon, oxygen, silicon, and elements all the way up to iron. Even heavier elements like gold, platinum, and uranium were created in the neutron-rich environment of the explosion itself. When these supernovae blasted their contents into space, they seeded the surrounding gas clouds with these newly forged elements. For the first time, the universe contained significant amounts of elements other than hydrogen and helium. Astronomers refer to all elements heavier than helium as metals, and this first enrichment of the cosmos with metals would change everything that followed. The debris from these explosions mixed with surrounding gas clouds, creating a slightly more complex chemical environment. Gas clouds enriched with these heavier elements could cool more efficiently, allowing smaller clumps to collapse into new stars. This led to the birth of the second generation of stars, called Population 2. These Population 2 stars, while still metal-poor by modern standards, contained enough carbon, oxygen, and other elements to evolve differently than their Population 3 predecessors. They could form with a wider range of masses. The smallest among them, red dwarfs with perhaps a tenth of the Sun's mass, burn their fuel so slowly that many of the first Population 2 stars are still shining today, nearly 14 billion years later. They are the oldest objects we can still observe directly, living fossils from the dawn of time. As Population 2 stars formed and evolved, they further enriched the interstellar medium with heavy elements when they died. Each generation of stars increased the metal content of the gas from which the next generation would form. This gradual enrichment eventually led to Population 1 stars like our Sun, with enough heavy elements to form rocky planets like Earth. But we are getting ahead of our story. Let us return to those first billion years after the Big Bang, when the universe was still young and the structures that would become galaxies were just beginning to take shape. The first stars did not form in isolation. They clustered together in the densest regions of the cosmic web, where filaments of dark matter and gas intersected. These stellar nurseries became the seeds of the first protogalaxies, collections of stars held together by their mutual gravitational attraction. These protogalaxies were small by modern standards, perhaps only a few thousand light years across and containing millions rather than billions of stars. They were also irregular in shape, lacking the structured spirals or ellipticals we see today. Their appearance was more like a swarm of stars, chaotic and constantly changing as new stars formed and old ones died in supernova explosions. Within these early stellar swarms, another process was underway. When the most massive stars died, some left behind black holes. These stellar mass black holes were small compared to the supermassive black holes we find at the centers of galaxies today, but they were seeds that could grow. As gas fell into these black holes, it formed accretion disks, superheated material spiraling inward that released enormous amounts of energy. The most active of these feeding black holes appeared as quasars, objects so bright they could be seen across the entire observable universe. The energy released by quasars further heated and ionized the gas around them, contributing to the rionization of the universe. In some cases, black holes merged with one another, growing larger over time. Those that happened to reside near the gravitational centers of protogalaxies had access to more gas and grew faster. Eventually, supermassive black holes with millions or billions of times the mass of the Sun would form at the hearts of most large galaxies, including the Milky Way. The formation of the first galaxies was a complex dance of gravity, gas dynamics, star formation, and feedback from supernovae and black holes. As small protogalaxies formed along filaments of the cosmic web, they began to move toward one another, drawn by gravity. When they met, they merged, combining their stars and gas into larger structures. These mergers were violent events on a cosmic scale. The collision of two protogalaxies could trigger bursts of star formation as gas clouds were compressed. It could also disrupt the orbits of existing stars, sending some on new paths and ejecting others from the galaxy entirely. Each merger reshaped the resulting galaxy, altering its structure and composition. The early universe was a time of rapid change and growth. Within the first billion years after the Big Bang, the first stars had formed, lived, and died. The first protogalaxies had emerged, merged, and evolved. The intergalactic medium had begun to be reionized by the light of stars and quasars, and the chemical composition of the cosmos had been forever altered by the creation and dispersal of heavy elements. Among the countless protogalaxies forming during this epoch were the ones that would eventually merge to form the Milky Way. Our galaxy's oldest stars, which astronomers can still identify by their extremely low metal content, formed during this time. These ancient stellar fossils preserve a record of conditions in the early universe, their composition telling us about the first generation of stars that lived and died before them. The oldest globular clusters in our galaxy, spherical collections of hundreds of thousands of stars, also date from this era. These dense star clusters formed when huge clouds of gas collapsed and fragmented into many stars simultaneously. Some globular clusters may have initially been the cores of small protogalaxies that were later absorbed by the growing Milky Way, their outer stars stripped away, while their dense centers remained intact. By about 1 billion years after the Big Bang, the universe had undergone profound changes. The simple world of hydrogen and helium had given way to a more complex cosmos, with a variety of chemical elements and increasingly organized structures. Protogalaxies continued to form, grow, and merge. The cosmic web channeled gas into these young galaxies, fueling ongoing star formation. The light from these early galaxies and quasars continued to reionize the intergalactic medium, creating a transparent universe similar to what we see today. By about 1 billion years after the Big Bang, most of the hydrogen in the universe had been reionized, marking the end of the cosmic dark ages and the dawn of the era of galaxies. As spectacular as these developments were, they were just the beginning of the story of our galaxy. The Milky Way as we know it today would take shape over many billions of years through a complex history of mergers, accretion, and internal evolution. The earliest phases set the stage, creating the building blocks from which our galactic home would form. The universe was still young, just 1 billion years old, but already the raw materials and basic structures needed for galactic formation were in place. Stars had created the heavy elements. Dark matter halos had grown through mergers. Protogalaxies had formed and begun their long dance of collision and combination. From this cosmic cauldron, the structures we now recognize as true galaxies would emerge. Some would evolve into enormous ellipticals, others into graceful spirals, and still others into irregular forms. Each followed its own unique path, shaped by its initial conditions and subsequent history. The path that led to the Milky Way began with the merger of several of these early protogalaxies. Exactly how many contributed to our galaxy's formation is difficult to determine, but studies of the chemical composition and motion of the oldest stars in the Milky Way suggest that several distinct star-forming regions combined in the distant past. One of the remarkable aspects of galactic evolution is how long it takes. The processes that shape galaxies unfold over billions of years. Stars orbit the galactic center at speeds of hundreds of kilometers per second, yet it takes them hundreds of millions of years to complete a single orbit. Mergers between galaxies can take hundreds of millions to billions of years to complete. Waves of star formation rise and fall over spans of tens or hundreds of millions of years. From our human perspective, with lives measured in decades, these timescales are almost impossible to grasp. Yet in the 13.8 billion years since the Big Bang, there has been ample time for galaxies to form, evolve, and transform through multiple generations of stars and numerous mergers. As we look outward from Earth with our most powerful telescopes, we can see galaxies at different stages of this long evolutionary process. Some of the most distant objects visible are young galaxies, seen as they were just 1 billion years after the Big Bang. Closer to home, we see galaxies at intermediate stages of evolution. And in our local cosmic neighborhood, we see mature galaxies like the Milky Way and Andromeda. Each galaxy we observe is a single frame from its own cosmic movie, a snapshot of one moment in its long history. By studying galaxies at different distances, and thus different times in the past, due to the finite speed of light, astronomers can piece together the story of how galaxies evolve. What emerges from these studies is a picture of galaxies as dynamic, ever-changing systems. Far from being static collections of stars, galaxies grow, transform, and evolve throughout their long lives. They consume gas from their surroundings, convert it into stars, are enriched by the heavy elements created in stellar deaths, and grow through mergers with other galaxies. The story of the first stars and the first galaxies is, in a very real sense, our own origin story. The elements that make up our bodies were created in those early stellar furnaces. The galaxy we call home began to take shape during those first few billion years. The conditions that would eventually allow for the formation of our solar system and the emergence of life on Earth were established during this formative epoch. Another fascinating aspect of these first stars is their pure composition. Modern stars like our Sun contain dozens of elements in various proportions. The Sun is primarily hydrogen and helium, but about 2% of its mass consists of heavier elements like carbon, nitrogen, oxygen, iron, and many others. These elements affect how the star forms, how it evolves, and how it interacts with its environment. Population 3 stars, by contrast, were made almost exclusively of hydrogen and helium, with only trace amounts of lithium and beryllium created in the Big Bang. This pristine composition made them fundamentally different from any star in the universe today. Their surfaces were hotter, their interiors more extreme, and their lives more tumultuous. The universe has never again produced stars quite like these first giants. Once the first supernovae had enriched the cosmos with heavier elements, all subsequent stars formed from gas clouds containing at least some of these metals. Even the most metal-poor stars discovered in our galaxy's halo today, ancient relics from the early universe, still contain more heavy elements than those first stellar pioneers. Astronomers have never directly observed a true population 3 star. They lived and died so long ago that their light, traveling for billions of years, is too faint for even our most powerful telescopes to detect. Instead, scientists infer their properties from theoretical models and from the chemical composition of the second generation of stars that formed from gas enriched by their explosions. Despite never having seen one, we can be confident that these stars existed. The elements heavier than lithium that fill the universe today had to be created somewhere, and stellar nucleosynthesis is the only known process that can produce them in the required quantities. The first stars were the universe's first alchemists, transforming the simple elements of the Big Bang into the complex periodic table we know today. The transition from population 3 to population 2 stars marked a fundamental shift in the universe's stellar population. With each successive generation, stars formed from gas clouds containing a greater abundance and diversity of elements. This changing chemical environment altered not only the stars themselves, but also what could form around them. Our own solar system, with its rocky planets including Earth, could only exist because previous generations of stars had created and dispersed elements like silicon, iron, magnesium, and oxygen. The first stars contributed to this enrichment, beginning a process that would eventually lead to worlds where life could emerge. Another profound impact of the first stars was on the light of the universe itself. During the cosmic dark ages, the universe was filled with neutral hydrogen, which is highly effective at absorbing certain wavelengths of light. As the first stars and quasars began to ionize this hydrogen, the universe became increasingly transparent. This transition, known as reionization, was not instantaneous, but occurred gradually over hundreds of millions of years. It began around a few hundred million years after the Big Bang, with the formation of the first stars, and was largely complete by about 1 billion years after the Big Bang. The process of reionization started with isolated bubbles of ionized hydrogen around the first stars and quasars. As more and more stars formed, these bubbles expanded and eventually merged, creating a fully ionized intergalactic medium. This ionized state has persisted to the present day, allowing light to travel freely across the cosmos. The emerging protogalaxies of this era were laboratories for extreme physics. Star formation rates in some of these systems may have been hundreds or even thousands of times higher than in our galaxy today. Supernova explosions would have been commonplace, perhaps occurring somewhere in the protogalaxy every few years or even more frequently. These frequent supernovae had a profound impact on the evolution of protogalaxies. The energy they released could heat the surrounding gas, temporarily halting star formation in their vicinity. In smaller protogalaxies, the combined effect of many supernovae could even expel gas from the system entirely, quenching star formation throughout the protogalaxy. This process, known as supernova feedback, helped regulate the growth of early galaxies. Without it, protogalaxies might have converted all of their gas into stars very quickly, leaving nothing for later generations. Instead, feedback created a more measured pace of star formation, allowing protogalaxies to grow and evolve over billions of years. Supernova feedback was particularly important in shaping the earliest ancestors of the Milky Way. Our galaxy's oldest stars show a pattern of chemical abundances that suggests their formation was influenced by the explosions of the first generation of stars. The elements created in these explosions were not uniformly mixed, but created pockets of enriched gas with distinctive chemical signatures. As important as stars were in this early era, dark matter played an equally crucial role. The invisible scaffolding of dark matter halos provided the gravitational wells in which gas could accumulate and cool, leading to star formation. The merger of dark matter halos drove the merger of the protogalaxies they contained, building up larger structures over time. Studies of the current distribution of dark matter in and around the Milky Way suggest that our galaxy's dark matter halo formed from the merger of many smaller halos. This process of hierarchical assembly, where small structures combine to form larger ones, appears to be the primary way that both dark matter halos and the galaxies they host have grown throughout cosmic history. By about 1.5 billion years after the Big Bang, the basic architecture of what would become the Milky Way was beginning to take shape. A collection of protogalaxies, each containing populations of stars and gas, was orbiting within a common dark matter halo. Some had already merged, while others remained distinct but bound together by gravity. These mergers were not gentle processes. When two protogalaxies collided, their gas clouds smashed into one another, creating shock waves that compressed the gas and triggered bursts of star formation. Existing stars were flung onto new orbits by the changing gravitational field. In some cases, stars could be ejected from the system entirely, becoming intergalactic wanderers. The early Milky Way likely went through several such merger events, each reshaping its structure and composition. The evidence for these ancient mergers is still visible today in the motion and chemical composition of the oldest stars in our galaxy's halo. As the protogalaxies that would form the Milky Way merged and evolved, they began to develop the earliest versions of the structures we see in our galaxy today. Gas began to settle into a rotating disk, simply because rotation is conserved during the collapse of a gas cloud. Stars formed within this disk inherited its rotational motion, creating the first hint of what would eventually become the Milky Way's disk. At the same time, the random motions of stars from merged protogalaxies created a more spherical distribution around the disk. This would eventually evolve into the Milky Way's halo, a diffuse region of mostly ancient stars surrounding the more densely populated disk. The interplay between ordered rotation in the disk and random motion in the halo created a dynamic tension that would shape the evolving galaxy. Gas accreting onto the galaxy would generally settle into the disk due to conservation of angular momentum, feeding star formation there. Meanwhile, the halo would be enriched primarily by the absorption of smaller galaxies and star clusters. By 2 billion years after the Big Bang, about 12 billion years ago, the Milky Way had likely already acquired many of the features we recognize today, though in more rudimentary form. It had a rotating disk where new stars formed, a halo of older stars, and probably a central concentration of stars that would later develop into the galactic bulge. During this early phase of the Milky Way's history, star formation was much more vigorous than it is today. The galaxy was gas-rich, with streams of pristine and lightly enriched gas flowing in along filaments of the cosmic web. This abundant fuel-powered waves of star formation that illuminated the young galaxy with the blue light of massive, short-lived stars. These episodes of intense star formation, called starbursts, may have been triggered by the infall of gas or by mergers with other protogalaxies. During these events, the rate of star formation could increase by factors of 10 or more above the baseline rate, leading to the birth of millions of new stars in a relatively short time. The evidence for these ancient starbursts can be seen in populations of stars in our galaxy that share similar ages and chemical compositions. These stellar populations form together during specific episodes of star formation in the Milky Way's past, their properties frozen in time like geological strata that reveal Earth's history. As spectacular as these early phases of the Milky Way's evolution were, they were just the beginning of our galaxy's long story. Over the next 10 billion years, the Milky Way would continue to grow and change, developing the complex structure we see today through a combination of internal evolution and interactions with other galaxies. In the fire of ancient suns, the seeds of our galaxy were sown. Their light began a process that continues to this day, as the Milky Way evolves, forms new stars, and moves through the cosmos. The first chapter in our galactic story was written by those primordial giants, the population 3 stars, whose brief, brilliant lives forever changed the universe. As the universe approached its 2 billionth birthday, the foundations of our galactic home were taking shape. What would eventually become the Milky Way began not as a single entity, but as a collection of smaller protogalaxies orbiting within a common dark matter halo. These building blocks, themselves formed from the first generations of stars, were drawn together by gravity, destined to merge into something greater than the sum of their parts. The Milky Way's early ancestor, which astronomers sometimes call the Proto-Milky Way, was likely already the dominant galaxy in its local environment by this time. Its greater mass gave it a stronger gravitational pull, allowing it to draw in both gas from the cosmic web and smaller galaxies from its surroundings. This process of galactic cannibalism would continue throughout the Milky Way's history, but it was particularly active during these early times. Recent studies using data from the Webb Space Telescope have allowed astronomers to identify the remnants of some of these ancient mergers. By mapping the positions, motions, and chemical compositions of billions of stars, scientists can identify groups that likely originated in the same accreted dwarf galaxy. These stellar streams and associations are like fossil records, preserving the memory of galaxies long since absorbed into the Milky Way. One of the most significant early mergers occurred around 10 billion years ago, when a galaxy that astronomers have named Gaia Enceladus, or the Gaia Sausage, collided with the Proto-Milky Way. This collision was a major event in our galaxy's history, bringing in a large number of stars and a significant amount of gas. The stars from Gaia Enceladus can still be identified today by their distinctive motions and chemical compositions, a ghostly reminder of a galaxy that ceased to exist billions of years ago. But the Proto-Milky Way didn't just grow through mergers. It also accumulated gas directly from the cosmic web, the network of filaments and sheets of dark matter and gas that forms the largest scale structure in the universe. These filaments acted like cosmic highways, channeling pristine or lightly enriched gas toward the growing galaxy. As this gas fell into the Proto-Milky Way's gravitational well, it gained kinetic energy, heating up as it was compressed. Before this gas could form stars, it needed to cool down. In the early universe, with few heavy elements, this cooling was primarily through the radiation of hydrogen and helium. As the universe became enriched with metals from the first generations of stars, additional cooling mechanisms became available, making the process more efficient. The cooling gas would naturally settle into a rotating disk due to the conservation of angular momentum. Any initial rotation in the gas cloud would be amplified as the cloud contracted, much like an ice skater spins faster when pulling in their arms. This rotation prevented the gas from collapsing directly toward the center of the galaxy, instead causing it to form a flattened, spinning structure. Within this early disk, pockets of gas became dense enough to collapse under their own gravity, forming new stars. Unlike the first stars in the universe, These were born from gas that had already been enriched with heavy elements from previous stellar generations. As a result, they had different properties and evolutionary paths than the population 3 stars that came before them. Star formation in the early Milky Way likely occurred in bursts. When gas flowed in from the cosmic web or a merger brought in fresh material, star formation rates would spike dramatically. These starbursts would light up the galaxy with the blue glow of massive, short-lived stars, making it much brighter than during quieter periods. These episodes of intense star formation reshaped the galaxy in multiple ways. The energy and momentum injected into the interstellar medium by massive stars and supernova could compress gas in some regions, triggering further star formation, while dispersing gas in others, temporarily halting stellar births. This complex feedback process helped regulate the galaxy's growth, preventing it from converting all its gas into stars too quickly. The chemical composition of the galaxy also evolved with each generation of stars. The first stars in the proto-Milky Way were extremely poor in elements heavier than helium, reflecting the limited enrichment of the universe at that time. As these stars lived and died, they added more metals to the interstellar medium, increasing the metallicity of subsequent stellar generations. This chemical evolution is recorded in the stars we see today. By measuring the abundance of various elements in a star's atmosphere, astronomers can determine when in the Milky Way's history it formed. The oldest stars, found primarily in the galactic halo and in globular clusters, have very low metallicities. Younger stars, like our Sun, have much higher metal content, reflecting billions of years of enrichment. The proto-Milky Way's growth wasn't limited to its stellar and gaseous components. At its center, a supermassive black hole was also growing. Like most large galaxies, the Milky Way hosts a central black hole, now known as Sagittarius A star, with a mass of about 4 million times that of the Sun. This black hole likely formed from the merger of smaller black holes that were at the centers of accreted dwarf galaxies, combined with direct accretion of gas. During the proto-Milky Way phase, this central black hole may have been much more active than it is today. As gas flowed toward the galactic center, some would have been captured by the black hole's gravity, forming an accretion disk of superheated material spiraling inward. The energy released by this process could have made the young Milky Way's core temporarily shine as an active galactic nucleus, possibly even as a quasar during periods of particularly high accretion. The energy and radiation from this active phase would have influenced the galaxy's evolution. Powerful outflows from the region around the black hole could have heated or even expelled gas from the inner parts of the galaxy, regulating both star formation and the black hole's own growth. This process, known as active galactic nucleus feedback, is another of the complex regulatory mechanisms that shape galactic evolution. By about 3 billion years after the Big Bang, the proto-Milky Way had likely developed a recognizable structure, with a rotating disk of gas and younger stars, a more spherical halo of older stars, and a central concentration that would evolve into the bulge. This basic architecture would persist through the rest of the galaxy's history, though its details would continue to change. The disk was probably smaller and thicker than the one we see today, perhaps 10 to 15,000 light-years in radius, rather than the current 50,000. It would have been more turbulent, with stars moving in less orderly orbits, reflecting the chaotic conditions of the early galaxy. Over time, as the Milky Way grew and evolved, the disk would expand and thin out, developing the more ordered structure we observe now. The halo at this stage would have been relatively rich in gas compared to today's nearly gas-free halo. It would have contained a mix of stars formed within the proto-Milky Way and those accreted from merged galaxies. Globular clusters, dense spherical collections of hundreds of thousands of stars, would have orbited within this halo, some formed in situ and others brought in by accreted dwarf galaxies. As the universe approached its 4 billionth birthday, about 10 billion years ago, the Milky Way entered a phase of particularly intense merger activity. Several significant collisions with smaller galaxies occurred during this period, each adding stars, gas, and dark matter to our growing galaxy. These mergers weren't just simple additions of material. They fundamentally reshaped the Milky Way, altering the orbits of existing stars, triggering new waves of star formation, and even changing the orientation of the galactic disk. The evidence for these violent events is still visible in the complex structure of our galaxy's halo and in the stellar streams that wind through it. One of the most significant mergers of this period was with the galaxy astronomers called Kraken or Heracles, which may have been even more massive than the Gaia-Enceladus system mentioned earlier. This collision, which occurred about 10 to 11 billion years ago, likely brought in a substantial fraction of the stars now found in the Milky Way's inner halo and bulge. Another major merger from this period involved a galaxy called Sequoia, which left behind a distinctive trail of stars and globular clusters that orbit the Milky Way in a direction opposite to the rotation of the disk. This retrograde motion is a telling sign of an accreted system, as stars formed within the Milky Way would generally orbit in the same direction as the disk. These mergers, along with several others that have been identified, contributed to a period of intense transformation in the Milky Way's history. By studying the remnants of these accreted galaxies, astronomers are piecing together the complex puzzle of our galaxy's assembly history, building a more detailed picture of how the Milky Way grew over cosmic time. While these dramatic merger events were occurring, a more gradual process of gas accretion continued. Filaments of the cosmic web funneled hydrogen and helium into the Milky Way, providing fresh fuel for star formation. This gas, falling into the galaxy's gravitational well, would cool and eventually settle into the disk, where it could collapse to form new stars. The interaction between this inflowing gas and the existing material in the galaxy was complex. In some cases, the infalling gas would collide with gas already in the disk, creating shock waves that compressed the material and triggered star formation. In other cases, it might disrupt existing star-forming regions or even eject some gas from the galaxy entirely. This delicate balance between gas inflow, star formation, and feedback from stars and the central black hole regulated the Milky Way's growth. Too much inflow without sufficient feedback would have led to runaway star formation, depleting the galaxy's gas supply too quickly. Too much feedback without adequate inflow would have quenched star formation prematurely, leaving the Milky Way smaller and less luminous than it is today. The fact that our galaxy found a middle path, maintaining star formation for over 13 billion years while growing to its current massive size, is a testament to the effectiveness of these regulatory mechanisms. The Milky Way evolved as a self-regulating system, its various components and processes achieving a dynamic equilibrium that allowed for sustained but controlled growth. By about 8 billion years ago, the Milky Way had acquired much of its current mass, though its structure continued to evolve. The most dramatic merger events were largely complete, though smaller acquisitions would continue throughout the galaxy's history, and indeed are still occurring today. Star formation had begun to slow from its early peak, but remained active, particularly in the disk. During this more mature phase of the Milky Way's evolution, internal processes became increasingly important in shaping the galaxy's structure. The collective gravitational effects of stars, gas clouds, and dark matter drove the formation and evolution of large-scale features like spiral arms and the central bar. Spiral arms, the graceful, winding structures that give spiral galaxies their name, are not fixed features but rather wave patterns that move through the galactic disk. They are created by density waves, regions where stars and gas are temporarily compressed as they orbit the galactic center. These compression regions trigger star formation, which is why spiral arms appear bright and blue, illuminated by the light of newly formed massive stars. The Milky Way's spiral structure likely evolved gradually over billions of years. In the early, more chaotic galaxy, any spiral pattern would have been less organized and more transient. As the galaxy settled into a more stable state, with a thinner, more orderly disk, more persistent spiral arms could develop and maintain themselves through the galaxy's self-gravity. The central bar, a straight or slightly curved structure extending outward from the galactic center, also developed during this period. Bars are common features in spiral galaxies, including the Milky Way, and form through natural gravitational instabilities in the disk. Once formed, a bar can profoundly influence the galaxy's evolution, funneling gas toward the center and altering the orbits of stars throughout the disk. The interplay between these large-scale structures, the continued accretion of gas and small galaxies, and the ongoing processes of star formation and stellar death shaped the Milky Way into the galaxy we see today. Each of these factors left its mark on the galaxy's current structure, from the distribution of stars of different ages and metallicities to the pattern of gas and dust throughout the disk. Our own solar system formed relatively late in this history, about 4.5 billion years ago. By this time, the Milky Way had already undergone most of its major formative events. The gas cloud that collapsed to form the Sun and planets was enriched with heavy elements from many generations of previous stars, giving our solar system the chemical diversity needed for rocky planets and eventually life to develop. The Sun formed in a spiral arm of the Milky Way, in a region of the disk where conditions were right for the collapse of a gas cloud into a new stellar system. This location, about 27,000 light-years from the galactic center, places us in what astronomers call the Orion Arm, or local spur, a relatively minor spiral arm compared to the galaxy's major structures. From our vantage point within the disk, embedded in a spiral arm and surrounded by gas and dust, we cannot see the full majesty of our galactic home. Our view of much of the Milky Way is obscured by the very material from which stars are born. It is only through careful observation, using multiple wavelengths of light that can penetrate this obscuring material, that astronomers have been able to map the true structure of our galaxy. The picture that emerges from these studies is of a barred spiral galaxy, about 100,000 light-years in diameter, containing somewhere between 100 billion and 400 billion stars. The exact number remains uncertain due to the difficulty of counting the faintest and most distant stars. The Milky Way's disk is remarkably thin for its diameter, with most of the material concentrated in a layer just 1,000 light-years thick. Surrounding this disk is a much more diffuse halo of stars and globular clusters, extending perhaps 200,000 light-years in all directions. This halo contains some of the oldest stars in the galaxy, many of which were born in smaller galaxies that were later accreted by the Milky Way. The halo also includes vast amounts of dark matter, the invisible substance that makes up most of the galaxy's mass, and extends even farther into space than the visible components. At the very center of this vast structure lies the supermassive black hole, Sagittarius A star, surrounded by a dense cluster of stars that orbit it at tremendous speeds. This central region, known as the nuclear star cluster, is one of the most extreme environments in the galaxy, with stellar densities thousands of times higher than in our local neighborhood. The journey from the proto-Milky Way to the galaxy we see today spans more than 10 billion years of cosmic history. It is a story of growth through both peaceful accretion and violent mergers, of internal evolution driven by the complex interplay of gravity, gas dynamics, and stellar feedback, and of chemical enrichment through countless generations of stars, living and dying. This journey is recorded in the stars themselves. Each star in the Milky Way carries information about the time and place of its birth in its motion, its chemical composition, and its age. By studying large populations of stars, astronomers can read this record, piecing together the complex history of our galactic home. Modern surveys like Gaia, which has measured the positions and motions of more than 1 billion stars, are revolutionizing our understanding of this history. They reveal the Milky Way not as a static, unchanging structure, but as a dynamic, ever-evolving system, shaped by both internal processes and interactions with its environment. The story of the Milky Way's formation and evolution is far from complete. Many questions remain about the details of its assembly history, the nature and distribution of dark matter within it, and the role of various physical processes in shaping its current structure. But the broad outlines of this cosmic narrative, from the first proto-galactic fragments to the majestic spiral we inhabit today, are becoming increasingly clear. As we continue our journey through the history of the Milky Way, we will explore in more detail some of the key processes and events that shaped our galaxy. We will see how the disk formed and evolved, how the spiral arms and central bar developed, and how mergers with other galaxies transformed the Milky Way's structure. We will also look ahead to the future, to the next chapter in our galaxy's long story. For now, let us pause to appreciate the remarkable journey that has brought us to this point. From the first glimmers of structure in the early universe, through the formation of the first stars and proto-galaxies, to the emergence of the proto-Milky Way, Our galaxy's history is a testament to the creative power of gravity and the transformative effects of stellar birth and death. Piece by piece, the Milky Way was built not in silence but in storms of light. As the young Milky Way continued its evolution, a remarkable transformation began to unfold. The chaotic assembly of stars and gas clouds that formed the proto-galaxy gradually began to settle into a more ordered structure. This transition, occurring roughly 10 billion years ago, marked the beginning of one of the Milky Way's most distinctive features: its disk. The birth of the galactic disk was not a sudden event, but a gradual process driven by the fundamental laws of physics. As gas continued to fall into the growing galaxy from the cosmic web, it brought with it not just mass but also angular momentum, a measure of its rotational motion. This angular momentum could not simply disappear. When a rotating cloud of gas collapses under gravity, conservation of angular momentum causes it to spin faster, just as an ice skater spins more rapidly when pulling in their arms. However, this same principle prevents the cloud from collapsing completely to the center. Instead, it flattens out, forming a rotating disk. This process happened on a galactic scale in the early Milky Way. Gas falling into the galaxy's gravitational well conserved its angular momentum, preventing it from collapsing directly to the center. Instead, it settled into a vast, rotating disk around the galactic core. The formation of this disk was not uniform or peaceful. The inflowing gas collided with material already present in the galaxy, creating shockwaves that compressed the gas and triggered bursts of star formation. These collisions also dissipated energy, allowing the gas to settle more completely into the disk plane. The earliest disk was likely quite different from the one we see today. It was thicker, more turbulent, and probably smaller in diameter. Astronomers refer to this early structure as the thick disk, and remarkably, it still exists today as a distinct component of our galaxy. The thick disk formed during a chaotic period in the Milky Way's history, when mergers with other galaxies were still frequent and gas accretion rates were high. Stars born in this environment inherited the turbulent, somewhat disordered motions of their parent gas clouds. As a result, they move in orbits that take them relatively far above and below the main plane of the galaxy. These thick disk stars are also chemically distinct from those that would form later. They tend to be poorer in what astronomers call metals, elements heavier than hydrogen and helium. This reflects the lower level of chemical enrichment in the early galaxy, before many generations of stars had lived and died, creating and dispersing heavier elements. The formation of the thick disk was likely accelerated by a significant merger event that occurred around 10 billion years ago. Astronomers have identified the remnants of a galaxy they call Gaia Enceladus, or the Gaia sausage, which collided with the Milky Way during this period. This collision would have stirred up the existing gas and stars, increasing the thickness and turbulence of the forming disk. As the merger rate declined and the galaxy's evolution became more internally driven, a new phase in the disk's formation began. Gas continuing to accrete onto the galaxy could cool more efficiently, partly due to the increasing abundance of heavy elements that enhanced the cooling process. This cooling allowed the gas to settle into an increasingly thin layer. Stars born in this more settled environment inherited the more orderly, circular orbits of their parent gas clouds. These stars form what astronomers call the thin disk, which contains most of the visible matter in the Milky Way today. Our own Sun, born about 4.5 billion years ago, is a thin disk star. The transition from thick disk to thin disk formation was not sudden but gradual, occurring over billions of years. Even today, both components exist as distinct populations within our galaxy, their different properties preserving a record of the Milky Way's evolutionary history. The thin disk, where most star formation occurs today, is remarkably flat, given its vast extent. While the disk spans about 100,000 light-years in diameter, most of its material is concentrated within a layer just 1,000 light-years thick, less than 1% of its width. This extreme flatness is a testament to how completely the gas was able to settle into a plane as the galaxy evolved. Within this thin disk, gas and stars orbit the galactic center in nearly circular paths. The entire structure rotates, with material closer to the center moving faster to complete an orbit than material further out. Our Sun, located about 27,000 light-years from the center, takes about 230 million years to complete one orbit around the galaxy. This differential rotation, where different parts of the disk rotate at different rates, plays a crucial role in the formation of spiral arms, another key feature of the Milky Way's disk. But before we explore the rise of the spiral structure, let's look more closely at how star formation evolved as the disk formed. In the early turbulent disk, star formation was likely more vigorous and chaotic than it is today. Gas clouds were more massive and more easily compressed by collisions and the effects of supernovae. This led to the formation of stars across a wide range of masses, including many massive stars that lived fast, died young, and enriched their surroundings with heavy elements. As the disk settled and became thinner, star formation became more organized but still robust. Gas began to concentrate in spiral patterns, creating the ideal conditions for the birth of new stars. These spiral arms became the primary sites of star formation in the mature galaxy. The process of star formation in the disk follows a cycle that continues to this day. Clouds of molecular hydrogen, some containing enough mass to form thousands of stars, collapse under their own gravity. As they collapse, they fragment into smaller clumps, each of which may form a star or a small cluster of stars. The most massive stars in these new stellar nurseries burn hot and bright, emitting intense ultraviolet radiation that ionizes the surrounding gas, creating glowing regions called HII regions or emission nebulae. These stars live fast and die young, exploding as supernovae after just a few million years. These supernova explosions have profound effects on their surroundings. They inject energy and momentum into nearby gas, sometimes triggering the collapse of adjacent clouds and the birth of new stars. They also enrich the interstellar medium with heavy elements forged in their cores and during the explosion itself, increasing the metallicity of the next generation of stars. This cycle of star birth, stellar evolution, and stellar death has continued for billions of years in the Milky Way's disk, gradually building up the complex ecosystem of stars, gas, and dust that we observe today. Throughout this long history, the chemical composition of the disk has evolved, with each generation of stars inheriting a slightly different mix of elements than the one before. Astronomers can trace this chemical evolution through careful studies of stars of different ages. The oldest stars in the disk have lower abundances of heavy elements, reflecting the lower level of enrichment in the early galaxy. Younger stars, like our Sun, have higher metallicities, incorporating the products of many generations of stellar nucleosynthesis. This chemical evolution has important implications for the types of planetary systems that can form around stars of different ages. The earliest stars in the disk likely had few, if any, rocky planets, as the elements needed to form such worlds, like silicon, iron, and carbon, were not yet abundant. As the disk evolved and became enriched with these elements, the formation of rocky planets like Earth became possible. Our own solar system, forming relatively late in the Milky Way's history, benefited from this long chemical evolution. The Sun and its planets incorporated elements created in countless stars that lived and died over the preceding 9 billion years. In a very real sense, we are made of star stuff, our bodies containing atoms forged in stellar furnaces long before our Sun began to shine. As the disk evolved, it developed increasingly complex structure. Perhaps the most striking feature of the modern Milky Way's disk is its spiral pattern, a series of graceful arms winding outward from the galaxy's center. These spiral arms are not static structures, but rather density waves that move through the disk, temporarily compressing the gas and stars as they pass. The exact mechanism that generates and maintains these spiral patterns is still a subject of active research, but several processes likely contribute. The differential rotation of the disk naturally tends to create spiral patterns from any initial perturbation. The gravity of nearby dwarf galaxies can also excite spiral structure as they orbit the Milky Way. And once formed, the self-gravity of the spiral arms themselves helps to sustain the pattern. In the modern Milky Way, we can identify several major spiral arms. The Sun is located in what astronomers call the Orion arm or local spur, a relatively minor arm or spur between two major arms, the Perseus arm and the Sagittarius arm. These spiral features are most clearly traced by the distribution of young stars and star-forming regions, which illuminate the arms with their bright blue light. Another key structure that developed in the disk is the central bar. The Milky Way, like many spiral galaxies, is not a perfect spiral, but rather a barred spiral, with a straight or slightly curved bar of stars and gas extending outward from the galaxy's center. This bar rotates as a solid structure at a different rate than the surrounding disk. The formation of the bar, like the spiral arms, is thought to arise naturally from the self-gravity of the disk. Small initial asymmetries can grow over time through a process called the bar instability, eventually leading to the formation of a strong bar structure. Once formed, the bar significantly influences the evolution of the galaxy, driving gas inward toward the center and affecting the orbits of stars throughout the disk. The interplay between the bar and the spiral arms creates a dynamic, evolving structure. The bar can drive and maintain spiral arms, while interactions with passing satellite galaxies can strengthen or disrupt both features. The Milky Way's disk is not a static structure, but rather a dynamic, ever-changing system. As the disk evolved and the merger rate decreased, the Milky Way entered a more quiescent phase of its history. Star formation continued, but at a more measured pace than during the turbulent early period. The disk gradually grew in size through both the accretion of new material and the rearrangement of existing stars and gas. One important process in this later evolution is known as radial migration. Stars born in one part of the disk can gradually shift to larger or smaller orbital radii through interactions with the spiral arms and the central bar. This process mixes stars of different ages and chemical compositions throughout the disk, complicating the galaxy's evolutionary history, but also providing valuable clues for astronomers attempting to reconstruct that history. Another important process in the disk's evolution is the continued accretion of smaller galaxies. While major mergers became less frequent as the universe aged, the Milky Way continues to absorb smaller satellite galaxies to this day. These minor mergers can have significant effects on the disk, causing it to warp, flare at the edges, or develop other asymmetries. One such ongoing accretion event involves the Sagittarius Dwarf spheroidal galaxy, a small satellite galaxy currently being torn apart by the Milky Way's gravitational pull. As this galaxy makes repeated passes through the Milky Way's disk, it deposits stars in a vast stream that wraps around our galaxy multiple times. It also perturbs the disk, possibly exciting spiral structure and causing a noticeable warp in the outer regions. The cumulative effect of these processes over billions of years has created the complex, multi-component disk we observe today. The modern Milky Way's disk contains stars of all ages, from ancient ones formed over 10 billion years ago to young stars being born at this very moment. It shows a wealth of structure, from the grand design of the spiral arms to smaller features like spurs, feathers, and rings. Despite this complexity, the disk shows remarkable regularity in some of its properties. The distribution of stars and gas follows predictable patterns, with density decreasing exponentially with distance from the center. The chemical composition of disk stars shows clear trends with both radius and age, reflecting the inside-out growth of the disk and its chemical enrichment over time. This balance between order and complexity makes the Milky Way's disk a fascinating laboratory for studying galaxy evolution. By carefully mapping the positions, motions, ages, and chemical compositions of stars throughout the disk, astronomers can reconstruct the galaxy's history, understanding both the broad patterns of its evolution and the specific events that shaped it. The formation and evolution of the disk also played a crucial role in setting the stage for the emergence of life in our galaxy. The quiet, orderly environment of the thin disk, with its relatively circular stellar orbits, provides stable conditions where planetary systems can form and evolve undisturbed for billions of years. Our own solar system, located in a relatively quiet neighborhood about 2/3 of the way from the galactic center to the edge of the disk, has benefited from this stability. The Sun has completed about 20 orbits of the galaxy since its formation, maintaining a nearly circular path that keeps it away from the more disruptive regions near the galactic center or in the spiral arms. This stability, combined with the chemical enrichment that preceded the Sun's birth, created the conditions necessary for the formation of Earth and the eventual emergence of life. In this sense, the long, complex history of the Milky Way's disk is intimately connected to our own existence. As we look to the future, the evolution of the disk will continue. Star formation will gradually slow as the supply of gas diminishes, but it will likely continue for many billions of years. The disk will continue to grow through both internal processes and the accretion of satellite galaxies. And eventually, in about 4 billion years, a more dramatic transformation will begin when the Milky Way collides with the approaching Andromeda galaxy. But that is a story for a later chapter. For now, let us appreciate the remarkable structure that has developed over billions of years of galactic evolution. The Milky Way's disk, with its delicate spiral arms and orderly rotation, stands as a testament to the organizing power of gravity and the complex interplay of physical processes that shape galaxies. From the turbulent beginnings of the thick disk to the more orderly evolution of the thin disk. From the chaotic star formation of the early galaxy to the more measured pace of the present day, the story of the Milky Way's disk is a story of increasing order emerging from initial chaos. It is a story written in the stars themselves, in their motions, their compositions, and their ages. The formation of the Milky Way's disk also illustrates a broader pattern seen throughout the universe. The tendency for complex structures to emerge from simpler initial conditions through natural processes governed by physical laws. From the nearly uniform early universe, gravity and other forces have sculpted the rich tapestry of cosmic structure we see today, from galaxy clusters down to individual stars and planets. In the specific case of disk galaxies like the Milky Way, the key organizing principle is rotation. The conservation of angular momentum during the collapse of gas clouds naturally leads to the formation of rotating disks. This same principle operates across a wide range of scales in the universe, from the accretion disks around forming stars and black holes to the vast disks of spiral galaxies. The Milky Way's disk is not just a collection of stars and gas, but a dynamic ecosystem, with energy and matter flowing through it in complex patterns. Stars form from gas, live their lives, and return enriched material to the interstellar medium when they die. This cycle has repeated countless times throughout the galaxy's history, gradually building up the complex system we see today. The disk is also home to a rich variety of structures beyond stars and gas clouds. Dust lanes trace the spiral arms, absorbing light from stars behind them and glowing in infrared light. Supernova remnants, the expanding shells of gas and dust left behind by exploded stars, pepper the disk. Planetary nebulae, the beautiful glowing shells ejected by dying sun-like stars, add to the disk's complexity. Perhaps most remarkably, the disk contains countless planetary systems, each with its own unique architecture and history. While our own solar system is the only one we can study in detail from our vantage point, astronomical observations have revealed thousands of planets orbiting other stars in the galaxy, with many more awaiting discovery. These exoplanetary systems show a surprising diversity, from hot Jupiters orbiting perilously close to their stars, to super-Earths and mini-Neptunes, with no analogue in our solar system. Some systems contain multiple planets packed into orbits closer than Mercury is to our Sun, while others have giant planets in highly elongated orbits. This diversity suggests that planetary system formation is a complex process with many possible outcomes. Our own solar system, with its 4 inner rocky planets and 4 outer gas and ice giants, represents just one possible configuration among many. Its relatively orderly structure, with planets in nearly circular, well-spaced orbits, may be somewhat unusual, but the very existence of such a stable, long-lived planetary system depends on the environment provided by the Milky Way's disk. The story of the disk's formation and evolution is thus not just a tale of stars and gas on a galactic scale, but also a crucial part of our own origin story. The conditions that allowed for the formation of Earth and the emergence of life were set by billions of years of galactic evolution, creating both the elements needed for life and the stable environment where it could flourish. As the disk continues to evolve in the future, it will likely foster the formation of many more planetary systems, perhaps some hosting life of their own. The great cosmic cycle of star birth, stellar evolution, and stellar death will continue, creating new generations of stars from the recycled material of their predecessors. This ongoing evolution will gradually change the disk's properties. Star formation will slowly decline as the supply of gas diminishes. The metallicity of new stars will continue to increase as each generation adds more heavy elements to the interstellar medium. The disk may grow thicker over time as interactions with satellite galaxies and internal processes, heat up the stellar population, increasing the average height of stellar orbits above and below the disk plane. Despite these changes, the fundamental structure of the disk is likely to persist for billions of years to come. The balance between gravity, rotation, and the various feedback processes that regulate star formation has created a remarkably stable configuration that can endure for much of the universe's history. This stability, however, is not permanent. The approaching collision with the Andromeda Galaxy, currently about 2.5 million light-years away, but moving toward us, will eventually transform both galaxies. But even this dramatic transformation is part of the natural cycle of galactic evolution. Throughout the universe, galaxies grow and change through both internal processes and interactions with their surroundings. The Milky Way's disk, for all its current majesty, is just one chapter in our galaxy's long cosmic story. As we reflect on the birth and evolution of the Milky Way's disk, we are reminded of the profound connection between our own existence and the broader cosmic processes that shaped our galactic home. The same physical laws that govern the formation and evolution of galaxies also govern the formation of stars, planets, and ultimately life itself. In this sense, the story of the Milky Way's disk is not separate from our own story, but an integral part of it. We are not merely observers of this grand cosmic narrative, but participants in it, our very existence made possible by the long chain of events that transformed a chaotic cloud of primordial gas into the orderly, star-filled disk we call home. From swirling clouds, order began to rise, a disk of stars circling in harmony. Throughout cosmic history, galaxies have rarely evolved in isolation. The vast web of dark matter that forms the universe's hidden scaffold has guided galaxies toward one another since the earliest times. When these cosmic travelers meet, they dance a gravitational ballet that can last for billions of years, gradually drawing closer until they merge into a single, larger galaxy. Our Milky Way, majestic spiral that it is today, grew to its current grandeur through countless such encounters. This process of galactic cannibalism, where larger galaxies consume smaller ones, has been fundamental to the Milky Way's growth and evolution. Each merger event has left its mark on our galaxy, contributing stars, gas, and dark matter, while also triggering waves of new star formation and reshaping existing structures. By studying the aftermath of these ancient collisions, astronomers are piecing together our galaxy's complex assembly history. The evidence for the Milky Way's cannibalistic past is written in the stars themselves. Stars that originated in other galaxies can be identified by their distinct motions and chemical compositions, which differ from those of stars born within the Milky Way. These stellar immigrants often form coherent streams or shells in the galaxy's halo, ghostly remnants of once independent galaxies now absorbed into our own. Recent astronomical surveys, particularly the European Space Agency's Gaia mission, have revolutionized our understanding of the Milky Way's merger history. By precisely measuring the positions, motions, and properties of billions of stars, Gaia has revealed the signatures of numerous past mergers, some of which significantly transformed our galaxy. One of the most dramatic merger events in the Milky Way's history occurred approximately 10 billion years ago, when a galaxy that astronomers call Gaia Enceladus, or the Gaia Sausage, collided with our galaxy. At the time, the Milky Way was much smaller than it is today, perhaps only a quarter of its current mass. Gaia Enceladus was also substantial, with perhaps 20 to 30% of the Milky Way's mass at that time. When these two galaxies collided, the results were spectacular. The merger triggered intense bursts of star formation as gas clouds were compressed by the gravitational disturbances. Existing stars were flung onto new orbits, some gaining so much energy that they were ejected from the galaxy entirely. The Milky Way's disk, which had just begun to form, was heated and thickened by the gravitational turmoil. The stars that once belonged to Gaia Enceladus now form a significant component of the Milky Way's inner halo. Their orbits are highly elongated, plunging toward the galactic center and then back out again, creating a sausage-like shape in velocity space that gives this merger its whimsical nickname. By identifying these stars and mapping their distribution, astronomers can reconstruct the approximate size and structure of the consumed galaxy. But Gaia Enceladus was just one of many galaxies the Milky Way has devoured over its long history. Another significant merger, perhaps even more massive, involved a galaxy that astronomers call Kraken or Heracles. This collision may have occurred even earlier than the Gaia-Enceladus merger, perhaps 11 to 12 billion years ago, when the Milky Way was still in its infancy. The stars from the Kraken merger are more difficult to identify than those from Gaia-Enceladus, partly because the event occurred so long ago that the stellar orbits have had time to relax and mix with the Milky Way's native population. Nevertheless, careful analysis of the chemical compositions and orbital properties of the oldest stars in our galaxy has revealed the likely signature of this ancient collision. Other significant mergers have been identified as well. About 10 billion years ago, a galaxy now called Sequoia was consumed by the Milky Way. The stars from this merger orbit the galactic center in the opposite direction to the rotation of the disk, a strong indication that they came from an external source. Similarly, a galaxy called the Helmi Stream was absorbed around the same time, its stars now forming a distinct group with shared properties orbiting through the Milky Way's halo. More recently, perhaps 6 to 8 billion years ago, the Milky Way absorbed a galaxy that astronomers call the Virgo Radial Merger. The stars from this collision are still settling into their new home, their orbits primarily moving radially inward and outward from the galactic center rather than orbiting around it. These major mergers represent just the largest of the many galaxies the Milky Way has consumed. Dozens of smaller mergers have been identified, each contributing a modest number of stars to our galaxy. And the process continues to this day, with the Milky Way currently absorbing several small satellite galaxies. The most dramatic ongoing merger involves the Sagittarius Dwarf spheroidal galaxy, discovered in 1994. This small galaxy, which originally contained perhaps a billion stars, is currently passing through the disk of the Milky Way for at least the third time. Each passage has stripped away stars, forming a vast stream that completely encircles our galaxy. In another billion years or so, the Sagittarius Dwarf will be completely absorbed, its identity erased as its stars are fully incorporated into the Milky Way. The effect of these mergers extends far beyond simply adding new stars to our galaxy. When galaxies collide, they trigger complex chains of events that can fundamentally alter their structure and evolution. Gas clouds are compressed, igniting bursts of star formation. Existing stars are heated, causing disks to thicken. Central bulges can grow, and bars can be strengthened or disrupted. Even the supermassive black holes at the centers of the galaxies can be affected, sometimes merging to form a larger black hole. In the case of the Milky Way, these mergers have helped shape many of the features we observe today. The thick disk component, for example, was likely puffed up during the Gaia-Enceladus merger. Many of the globular clusters orbiting in the Milky Way's halo were actually formed in other galaxies and brought in during mergers. Even the central bulge and bar may have been influenced by the influx of stars and gas from consumed galaxies. Mergers also play a crucial role in a galaxy's chemical evolution. Different galaxies can have distinct chemical signatures based on their star formation histories. When a smaller galaxy is absorbed by the Milky Way, it brings with it stars with unique chemical compositions, increasing the diversity of stellar populations in our galaxy. By studying these chemical differences, astronomers can identify stars that likely originated in the same accreted galaxy, even if their orbits have since diverged. The globular clusters that orbit the Milky Way tell a particularly interesting story about our galaxy's merger history. These dense collections of hundreds of thousands of stars are among the oldest structures in the universe. Some formed within the Milky Way itself, but many others were born in smaller galaxies that were later consumed. By studying the ages, chemical compositions, and orbits of these globular clusters, astronomers can identify which ones likely share a common origin in an accreted galaxy. For example, several globular clusters have been associated with the Gaia-Enceladus merger, sharing distinctive chemical patterns and orbital properties. Others are linked to the Sagittarius Dwarf, the Sequoia merger, or other identified accretion events. Together, these clusters form a kind of fossil record of the Milky Way's cannibalistic history. The dark matter halos of merged galaxies also play an important role in this cosmic dance. Dark matter, the invisible substance that makes up about 85% of the matter in the universe, forms extended halos around galaxies. When galaxies merge, their dark matter halos combine, but this process is not always smooth or complete. Simulations suggest that the Milky Way's dark matter halo may contain numerous substructures, remnants of the halos of consumed galaxies that have not fully mixed with the main halo. These dark matter substructures can influence the dynamics of stars and gas in the Milky Way, creating subtle perturbations that astronomers are now beginning to detect. They may also affect the orbits of the Milky Way's satellite galaxies and the tidal streams created by disrupted satellites. By carefully mapping these effects, astronomers hope to better understand the distribution of dark matter in and around our galaxy. The merger history of the Milky Way follows a pattern seen throughout the universe, where galaxy formation proceeds hierarchically. Small structures form first, then merge to create larger ones, which in turn merge to form even larger structures. This hierarchy of mergers, guided by the gravitational pull of dark matter, has built up galaxies like the Milky Way over billions of years. Interestingly, the Milky Way's merger history appears to have been relatively quiet compared to some galaxies of similar mass. Studies of other spirals suggest that many have experienced more numerous or more recent major mergers than our galaxy. This relatively peaceful history may explain why the Milky Way has maintained its well-ordered disk structure rather than being transformed into an elliptical galaxy, as often happens after major mergers. That's not to say that the Milky Way's history has been entirely peaceful. The mergers it has experienced, particularly the Gaia-Enceladus collision, were violent events on a cosmic scale, involving hundreds of billions of stars and unimaginable amounts of gas and dark matter. But these events occurred long enough ago that the galaxy has had time to settle back into a relatively stable configuration. For the stars involved in these ancient collisions, the experience would have been less dramatic than one might imagine. Galaxies are mostly empty space, with vast distances between individual stars. Even during the height of a merger, direct collisions between stars are extremely rare. Instead, stars are affected by the changing gravitational field, which gradually alters their orbits over millions or billions of years. The gas component of merging galaxies tells a different story. Unlike stars, gas clouds can directly collide, creating shockwaves that compress the gas and trigger bursts of star formation. These collision-induced starbursts can be spectacular, temporarily increasing a galaxy's star formation rate by factors of 10 or more. Evidence for such starbursts can be seen in the age distribution of stars in the Milky Way, with some periods showing significantly higher star formation rates than others. One interesting aspect of the Milky Way's merger history is that most of the significant mergers appear to have occurred relatively early in the galaxy's history. Over the past 8 billion years or so, the Milky Way has only absorbed small satellite galaxies, not the more substantial systems like Gaia-Enceladus. This trend toward fewer major mergers in recent cosmic history is actually common throughout the universe, as galaxies have become more widely separated due to cosmic expansion. The future, however, holds one more major merger for the Milky Way. The Andromeda Galaxy, our nearest large galactic neighbor, is currently about 2.5 million light-years away, but moving toward us at about 110 kilometers per second. In about 4.5 billion years, Andromeda and the Milky Way will begin to merge, a process that will take perhaps 2 billion years to complete. This future merger with Andromeda will be unlike any the Milky Way has experienced before. Andromeda is slightly larger than our galaxy, with perhaps 1.5 times the Milky Way's mass. The beautiful spiral structures of both galaxies will be destroyed, their gas used up in an enormous burst of star formation, and their separate identities erased. But that is a story for a future chapter. For now, let us return to the Milky Way's past mergers and their ongoing influence on our galactic home. One of the most fascinating aspects of the Milky Way's merger history is how it has been preserved in the galaxy's current structure. The stars accreted from other galaxies have not been completely mixed throughout the Milky Way, but often retain some memory of their origin. They may form coherent streams, move on similar orbits, or share distinctive chemical patterns that link them to their original host galaxy. These stellar streams are like cosmic fossils, preserving information about galaxies that ceased to exist as independent entities billions of years ago. Some streams are relatively young and still tightly focused, like the prominent stream from the Sagittarius Dwarf galaxy. Others are ancient and have begun to disperse, their stars spreading out along similar orbits around the Milky Way, but no longer forming a visually distinct structure. By carefully mapping these streams and other substructures in the Milky Way's halo, astronomers can reconstruct much of our galaxy's merger history. They can estimate how many significant mergers have occurred, when they happened, and the approximate masses of the consumed galaxies. This archaeological approach to galactic evolution has revolutionized our understanding of how the Milky Way formed and grew over cosmic time. The Milky Way's halo, the diffuse region of stars and globular clusters surrounding the disk, is particularly rich in evidence of past mergers. Most of the stars in the halo are believed to have originated in other galaxies that were later absorbed by the Milky Way. By studying the chemical compositions, ages, and orbital properties of these halo stars, astronomers can group them according to their likely origin galaxies. What emerges from these studies is a picture of the Milky Way as a composite system, built up through the gradual accretion of many smaller galaxies. While most of the stars in the disk likely formed within the Milky Way itself, perhaps 50% or more of the stars in the halo may have originated in other galaxies. Our galaxy is thus a kind of cosmic melting pot, combining stars born in many different environments into a single, coherent structure. This accretion history has also influenced the Milky Way's chemical evolution. Each merged galaxy brought with it stars and gas, with distinctive chemical signatures, reflecting its own unique history of star formation and stellar death. As these materials mixed with those native to the Milky Way, they created the complex pattern of chemical abundances we observe in our galaxy today. Some of the elements in our own bodies may have been created in stars that originally belonged to other galaxies, later absorbed by the Milky Way. In this sense, galactic cannibalism is a crucial part of our own cosmic origin story. Without these mergers, the Milky Way would be smaller, contain fewer heavy elements, and might never have formed a planetary system like our solar system. The influence of mergers extends to the Milky Way's central regions as well. The supermassive black hole at the heart of our galaxy, Sagittarius A star, has likely grown in part through the addition of black holes from merged galaxies. Similarly, the central bulge, the spheroidal collection of stars around the galactic center, has been shaped by both stars formed in situ and stars added through mergers. Even the Milky Way's famous spiral arms may bear the imprint of past mergers. While spiral structure can arise naturally in disk galaxies through internal processes, interactions with other galaxies can trigger or enhance spiral patterns. The current spiral structure of the Milky Way may have been influenced by both internal dynamics and the gravitational effects of past mergers and ongoing interactions with satellite galaxies. As we look to the skies surrounding our galaxy, we can see that the process of galactic cannibalism continues to this day. The Milky Way is currently surrounded by dozens of smaller satellite galaxies, most of which are bound to it gravitationally and will eventually be absorbed. These range from the large and small Magellanic Clouds, irregular galaxies visible to the naked eye from the southern hemisphere, to tiny dwarf spheroidals containing just a few 100,000 stars. Many of these satellite galaxies are already being disrupted by the Milky Way's gravitational pull. Long streams of stars are being drawn out from several of these systems, the initial stages of their eventual absorption into our galaxy. By studying these ongoing accretion events, astronomers can observe galactic cannibalism in action, providing insights into how this process has shaped the Milky Way throughout its history. What makes this story of galactic growth through mergers so fascinating is that it links the Milky Way to the broader narrative of structure formation in the universe. The same hierarchical assembly process that built our galaxy has operated throughout cosmic history, forming galaxy clusters, superclusters, and the vast cosmic web that defines the largest structures in the universe. The Milky Way's merger history also connects to the story of star formation and chemical enrichment that ultimately led to the creation of our solar system and the emergence of life on Earth. Without the heavy elements created in generations of stars and distributed through mergers and other processes, the rocky planets of our solar system could not have formed. In this sense, the story of galactic cannibalism is our story. The mergers that built the Milky Way created the environment in which our Sun and its planets could form. They brought together the elements needed for life and created the stable, metal-rich disk in which our solar system has evolved undisturbed for 4.5 billion years. As we continue to explore the Milky Way's structure and history, we constantly uncover new evidence of past mergers and their influence on our galaxy. Each new survey reveals additional stellar streams, more coherent groups of accreted stars, and further details about how these mergers transformed the Milky Way over billions of years. This ongoing research is not just about understanding our galaxy's past, but also about predicting its future. By studying how the Milky Way has responded to past mergers, astronomers can better model how it will react to the upcoming collision with Andromeda. While this future merger lies billions of years ahead, the groundwork for understanding it is being laid by studies of the Milky Way's cannibalistic history. Galaxies grow not alone, but by devouring and remembering. Among the most striking features of the Milky Way, and indeed of many galaxies throughout the universe, are the graceful spiral arms that wind outward from the galactic center. These vast structures, spanning thousands of light years and containing billions of stars, give spiral galaxies their distinctive pinwheel appearance. Yet despite their visual prominence, spiral arms are not solid structures, but rather waves of increased density that move through the galactic disk like ripples on a pond. The story of how the Milky Way's spiral arms formed and evolved is a fascinating tale of gravity, gas dynamics, and stellar birth. It is a story that continues to unfold today, as our galaxy's spiral structure slowly changes over billions of years. To understand the origin of spiral arms, we must first consider the rotation of the galactic disk. Unlike a solid object like a vinyl record, where all parts rotate at the same angular speed, a galaxy's disk exhibits what astronomers call differential rotation. Stars and gas clouds closer to the center orbit more quickly than those farther out. Our Sun, located about 27,000 light-years from the galactic center, takes approximately 230 million years to complete one orbit. Stars closer to the center might complete an orbit in just 50 million years, while those in the outer disk might take 500 million years or more. This differential rotation would seem to pose a problem for any enduring structure, like a spiral arm. If a spiral pattern was simply made up of the same stars maintaining their relative positions, differential rotation would quickly wind it up too tightly, destroying the pattern within a few 100 million years. Yet we know that spiral galaxies can maintain their beautiful patterns for billions of years. How is this possible? The answer lies in understanding that spiral arms are not fixed structures composed of the same stars, but rather density waves that move through the disk, temporarily gathering stars and gas as they pass. Individual stars move through the spiral arms rather than staying within them. A useful analogy is a traffic jam on a highway. The jam itself may remain in one location, but the cars that make it up are constantly changing as new vehicles enter the congestion from behind and others exit from the front. In a similar way, spiral arms are regions where stars and gas clouds temporarily move closer together, increasing the local density. As gas clouds enter these regions of higher density, they can be compressed beyond their normal state, triggering the collapse of the cloud and the formation of new stars. This is why spiral arms appear bluer and brighter than the rest of the disk. They are illuminated by young, massive hot stars that recently formed in these density waves. The origin of these spiral density waves has been a subject of intense study for decades. Several mechanisms appear to contribute to their formation and maintenance. One important process involves what astronomers call gravitational instabilities. Small initial perturbations in the disk's density can be amplified by self-gravity, where regions of slightly higher density attract more material, becoming even denser and creating a feedback loop. These instabilities naturally take on spiral patterns due to the disk's differential rotation. What might start as a small, localized density enhancement gets stretched into a spiral shape as the inner parts orbit faster than the outer parts. This process alone could not maintain spiral arms for billions of years, as the patterns would still wind up too tightly over time. But other processes come into play to sustain the spiral structure. One such process involves resonances within the disk. Certain orbital radii have special relationships to the rotation rate of the spiral pattern itself. At these resonances, Stars and gas can exchange energy and angular momentum with the spiral density wave, reinforcing the pattern. The most important of these is the corrotation resonance, where stars orbit at the same rate as the spiral pattern rotates, allowing for a sustained interaction that can maintain the spiral structure. Another factor that can trigger and enhance spiral arms is the gravitational influence of satellite galaxies. The Milky Way is surrounded by dozens of smaller galaxies, the largest being the Large and Small Magellanic Clouds. As these satellites orbit the Milky Way, their gravity tugs on the disk, creating disturbances that can excite spiral patterns. The ongoing disruption of the Sagittarius Dwarf spheroidal galaxy, which is currently passing through the Milky Way's disk, may be contributing to our galaxy's current spiral structure. The central bar of the Milky Way also plays a crucial role in maintaining spiral arms. The Milky Way is what astronomers call a barred spiral galaxy, with an elongated bar of stars and gas extending outward from the center. This bar rotates as a solid structure at a different rate than the surrounding disk. The gravitational influence of the bar can drive and maintain spiral arms, particularly the ones that appear to connect to the ends of the bar. Through a combination of these processes, the Milky Way has developed and maintained its beautiful spiral structure over billions of years. But this structure is not static. It evolves and changes as the galaxy ages, as its gas content decreases, and as it interacts with its environment. The current structure of the Milky Way's spiral arms has been challenging to map from our position within the disk. Unlike external galaxies, which we can observe in their entirety from the outside, we must piece together the Milky Way structure by observing different sections and combining the data. Nevertheless, astronomers have identified several major spiral arms in our galaxy. The most prominent spiral arms in the Milky Way include the Perseus arm, the outer arm, the Sagittarius arm, and the Scutum Centaurus arm. Our Sun is located in a smaller structure called the Orion arm, or local spur, which is a minor arm or branch between the Perseus and Sagittarius arms. These structures are most clearly traced by young, bright stars, star-forming regions, and gas clouds, as these components most strongly respond to the spiral density waves. The spiral arms are not perfectly symmetric or evenly spaced. Some are more prominent than others, and they vary in length, width, and the degree to which they are wound around the galactic center. This asymmetry is common in spiral galaxies and may reflect both internal dynamics and the influence of past interactions with other galaxies. The Milky Way's spiral arms are homes to some of the most spectacular sights in our galaxy. Within them lie vast star-forming regions where thousands of stars are born together from giant molecular clouds. These stellar nurseries, with names like the Orion Nebula, the Eagle Nebula, and the Carina Nebula, are among the most beautiful and complex structures in the cosmos. As a spiral density wave moves through the galactic disk, it compresses the gas clouds it encounters. In regions where the gas becomes dense enough, gravity overcomes the cloud's internal pressure and magnetic fields, causing it to collapse. The collapsing cloud fragments into smaller clumps, each of which may form one or more stars. The most massive of these newborn stars emit intense ultraviolet radiation that ionizes the surrounding gas, causing it to glow brightly as an emission nebula. These massive stars live fast and die young, lasting only a few million years before exploding as supernova. During their brief lives, their radiation and stellar winds can both trigger and suppress further star formation in their vicinity. After their deaths, their remains enrich the surrounding medium with heavy elements forged in their cores and during the supernova explosion. This cycle of star birth, stellar evolution, and stellar death has continued within the Milky Way's spiral arms for billions of years. Each generation of stars changes the composition and properties of the interstellar medium from which the next generation will form. Over time, the abundance of heavy elements increases, allowing for the formation of rocky planets like Earth around newer stars. The Sun and our solar system formed in a spiral arm about 4.5 billion years ago from a cloud of gas enriched by previous generations of stars. Since then, the Sun has completed about 20 orbits of the galactic center and has passed through multiple spiral arms. Currently, we are located in the relatively small Orion arm between two major arms. The passage of our solar system through spiral arms occurs every few hundred million years, and may have influenced Earth's history. Some scientists have suggested that encounters with spiral arms could increase the rate of comet impacts on Earth, potentially contributing to mass extinction events. While this hypothesis remains controversial, it highlights the ongoing relationship between our planet and the larger galactic structures in which it resides. The appearance of spiral arms varies depending on the wavelength of light used to observe them. In visible light, dominated by the blue glow of young, massive stars, the arms appear as distinct high-contrast features. In infrared light, which better reveals older stars, the spiral pattern is more subtle, as these stars have had time to move away from the density waves in which they formed. Radio observations, which trace the distribution of gas in the galaxy, show yet another view of the spiral structure. Cold molecular hydrogen, the primary component of the gas from which stars form, is difficult to detect directly but can be traced using carbon monoxide as a proxy. These observations reveal that the gas in spiral arms is not only denser, but also colder and more molecular than in the inter-arm regions, providing ideal conditions for star formation. The Milky Way's spiral structure is not a permanent feature, but will evolve significantly over the next few billion years. As the galaxy continues to convert gas into stars, the density of the interstellar medium will decrease, potentially weakening the spiral pattern. The inevitable collision with the Andromeda Galaxy, expected to begin in about 4.5 billion years, will eventually destroy the spiral structure entirely, transforming both galaxies into a single elliptical galaxy. But for now, the Milky Way's spiral arms remain a dominant feature of our galactic home. They are sites of creation, where new stars and planetary systems are born from the interstellar medium. They are highways of gas flow, channeling material through the disk, and they are timekeepers, their passage marking the slow rhythm of galactic evolution. From our perspective within the Orion Arm, we cannot directly see the full grandeur of the Milky Way's spiral structure. On a clear, dark night, far from city lights, we can observe the band of the Milky Way stretching across the sky, a hazy ribbon of light composed of countless distant stars. This band represents our edge-on view of the galactic disk, with the brightest portions corresponding to directions where we look along spiral arms. For most of human history, the true nature of this celestial band remained a mystery. It was only in the early 20th century that astronomers definitively established that the Milky Way is a galaxy, a vast island of stars separate from others, and that our Sun is just one of billions of stars within it. The realization that the Milky Way has a spiral structure came even later, pieced together through careful mapping of star distributions and gas clouds. Today, we continue to refine our understanding of the Milky Way's spiral structure through increasingly detailed observations. Space-based missions like Gaia are measuring the positions and motions of billions of stars with unprecedented precision, allowing astronomers to map the galaxy in 3 dimensions and track the movement of its components. What emerges from these studies is a picture of the Milky Way as a dynamic, evolving system. Its spiral arms are not static structures, but waves propagating through the disk, temporarily gathering stars and gas before releasing them again. They represent a kind of galactic heartbeat, rhythmically compressing gas into new stars as they have done for billions of years. The persistence of spiral structure in galaxies like the Milky Way is a testament to the self-organizing nature of complex systems under the influence of gravity. From the nearly uniform conditions of the early universe, gravity has sculpted increasingly complex structures, from the first stars and protogalaxies to the intricate spirals we see today. This evolution toward greater complexity is a common theme throughout the universe, from the formation of galaxies down to the emergence of life on Earth. In each case, energy flows and fundamental forces work to create and maintain ordered structures within a universe that tends toward overall disorder. The spiral arms of the Milky Way are perhaps the most beautiful example of this organizing principle at work on a galactic scale. They represent a kind of middle ground between chaos and order, between the random motions of individual stars and the elegant, galaxy-wide patterns that emerge from their collective behavior. As we contemplate the rise and evolution of the Milky Way's spiral arms, we are reminded of the interconnectedness of cosmic processes across vast scales of space and time. The same physical laws that govern the formation and evolution of galaxies also apply to stars, planets, and ultimately to life itself. We are not separate from these grand cosmic patterns, but an integral part of them, our very existence made possible by the long chain of events that transformed a chaotic cloud of primordial gas into the ordered, star-filled spiral we call home. Like ripples frozen in time, the arms of the Milky Way stretch across the void. At the heart of our vast spiral galaxy lies a region of extraordinary density, activity, and mystery. The galactic center, hidden from our direct view by thick clouds of dust, is a place where the extremes of the cosmos converge. Here, millions of stars are packed into a volume that would be nearly empty in our local neighborhood. Massive gas clouds swirl and collide. Magnetic fields twist and turn with unusual strength. And at the very core, a supermassive black hole, known as Sagittarius A star, quietly shapes the destiny of everything around it. The journey to our understanding of the galactic center has been a remarkable one. For most of human history, we had no idea it existed. The visible band of the Milky Way stretching across the night sky gave no obvious indication of a center, and the thick veil of dust in the galactic plane blocks visible light from this region, hiding it from our eyes. It was only with the advent of radio, infrared, and X-ray astronomy in the 20th century that we began to peer through this cosmic fog and glimpse the extraordinary environment at our galaxy's core. What these observations revealed was a region unlike any other in the Milky Way. The central few hundred light-years, sometimes called the central molecular zone, contains up to 10% of the galaxy's molecular gas, despite being less than 1% of the galaxy's diameter. This gas forms dense clouds that would be capable of forming millions of stars, if not for the turbulent environment that often prevents collapse. Surrounding this gas-rich region is the nuclear stellar bulge, a densely packed collection of stars extending about 1,000 light-years in all directions from the center. This region contains a mix of stellar populations, from ancient red giants to newly formed blue supergiants. The stars here orbit the galactic center at remarkable speeds, following paths that are more random and less ordered than the nearly circular orbits of stars in the disk. But it is the inner few light years that truly define the extreme nature of the galactic center. Here, a dense cluster of stars surrounds the supermassive black hole, Sagittarius. A star. This nuclear star cluster is one of the densest collections of stars in the galaxy. While in our solar neighborhood, the nearest star is over 4 light-years away. In the nuclear star cluster, thousands of stars would fit within that same volume. The stars in this central cluster orbit at tremendous speeds, some moving at thousands of kilometers per second due to the powerful gravitational pull of the black hole. Their orbits are not neatly circular like those of planets around the Sun, but are instead highly elongated ellipses that bring them perilously close to the black hole at their nearest approach. By carefully tracking the motions of these stars over many years, astronomers have been able to measure the mass of the central black hole with remarkable precision. Sagittarius. A star contains approximately 4 million times the mass of our Sun, concentrated in a region smaller than our solar system. This precise measurement was the culmination of decades of observation and earned the scientists involved the Nobel Prize in Physics in 2020. The supermassive black hole at the Milky Way's center is not particularly active by cosmic standards. Unlike the energetic quasars seen in distant galaxies, where supermassive black holes devour matter at prodigious rates and shine with the light of trillions of stars, Sagittarius. A star is relatively quiet. It accretes matter at a modest rate, producing only a faint glow across multiple wavelengths of light. This quiescence is somewhat puzzling given the abundance of gas in the galactic center. Theoretical models suggest that the black hole's feeding is limited by powerful outflows from nearby stars, which sweep away much of the gas that might otherwise fall in. Occasional flares of radiation from Sagittarius A star suggest that it does sometimes consume larger amounts of material, perhaps when gas clouds or small stars venture too close and are torn apart by tidal forces. Despite its current quiet state, there is evidence that Sagittarius A star was more active in the recent astronomical past. Observations of large bubbles of hot gas extending above and below the galactic plane, known as the Fermi bubbles, suggest that a major outburst from the black hole occurred a few million years ago. This event, perhaps triggered by the infall of a large gas cloud or the tidal disruption of a star, may have produced jets of energy that inflated these massive structures. The relationship between the supermassive black hole and its surroundings is complex and bidirectional. While the black hole's gravity profoundly influences the orbits of nearby stars and the flow of gas, the environment also affects the black hole's growth and activity. Star formation near the black hole can both provide fuel for accretion and generate winds that blow material away. The collective gravity of the nuclear star cluster competes with that of the black hole in shaping orbits slightly further out. One of the most fascinating aspects of the galactic center is the ongoing star formation in this extreme environment. Despite the turbulent conditions and strong tidal forces from the black hole, young stars are found even in the central parsec, the region within about 3 light years of Sagittarius A star. These stars include massive, short-lived types that must have formed recently within the past few million years. How stars form in this region remains something of a puzzle. The tidal forces from the black hole should tear apart gas clouds before they can collapse to form stars, at least in the innermost regions. One theory suggests that stars form further out, in a disk of gas circling the black hole, and then migrate inward. Another proposes that gas clouds on highly eccentric orbits can become compressed at their closest approach to the black hole, triggering collapse and star formation. Whatever the mechanism, the presence of these young stars indicates that the galactic center is a dynamic, evolving region. Star formation, stellar evolution, and occasional accretion events onto the black hole continuously reshape this environment on timescales ranging from years to millions of years. The properties of the nuclear star cluster surrounding Sagittarius A star provide important clues about the formation and evolution of the galactic center. The cluster contains stars of various ages, from ancient ones over 10 billion years old to newly formed stars just a few million years young. This age diversity suggests that star formation has occurred repeatedly in this region throughout the galaxy's history rather than in a single burst. The chemical composition of these stars also tells a story. Many show high abundances of heavy elements, indicating that they formed from gas that had been enriched by multiple generations of previous stars. This enrichment is more pronounced than in most parts of the galaxy, suggesting that the galactic center has experienced particularly intense cycles of star formation, stellar death, and reincorporation of enriched material into new stars. The central few parsecs also contain several unusual objects that highlight the extreme conditions in this region. A collection of stars known as the S stars orbit very close to the black hole, with periods as short as 16 years. These stars experience enormous tidal forces and move at up to a few % of the speed of light at their closest approach to Sagittarius A star. By tracking their precise orbits, astronomers can test Einstein's theory of general relativity in the strong gravity regime. Another intriguing feature is a structure known as the mini-spiral, a collection of streams of ionized gas flowing toward the central black hole. This material may be feeding the modest activity we observe from Sagittarius A star, and could occasionally lead to more dramatic accretion events when particularly dense clumps fall in. Surrounding these innermost regions is a ring of molecular gas called the circumnuclear disk, which orbits at a distance of about 5 to 10 light-years from the black hole. This ring contains enough gas to form thousands of stars, but its material appears to be too turbulent and too strongly affected by magnetic fields to collapse and form stars efficiently. Instead, it serves as a reservoir that occasionally feeds gas toward the black hole. Moving outward to scales of about 100 light-years from the center, we encounter a region filled with massive star clusters. These include the Arches cluster and the Quintuplet cluster, each containing thousands of stars, including some of the most massive and luminous known in our galaxy. These clusters are only a few million years old, evidence of a recent burst of star formation in this region. The presence of these massive clusters highlights another extreme aspect of the galactic center, the unusual conditions for star formation. Throughout most of the galaxy, stars typically form with a mixture of masses, with low-mass stars being much more common than high-mass ones. But in the galactic center, there appears to be a bias toward forming more massive stars. This may be due to the higher temperatures, pressures, and turbulence in the molecular clouds of this region, which require greater gravity and thus greater mass to overcome. The massive stars in these clusters have profound effects on their surroundings. Their intense radiation ionizes nearby gas, creating glowing nebulae. Their powerful stellar winds blow bubbles in the interstellar medium and inject energy that keeps the gas turbulent. And when they die, their supernova explosions further enrich and energize the environment. At distances of a few hundred light-years from the center lies the central molecular zone mentioned earlier. This region contains giant molecular clouds with names like Sagittarius B2, some of the most massive in the galaxy. These clouds are denser, hotter, and more turbulent than typical molecular clouds elsewhere in the Milky Way. Despite containing enough gas to form millions of stars, the central molecular zone forms stars at a lower rate than might be expected given its gas content. The reason appears to be the extreme turbulence in these clouds, driven by the complex dynamics of the galactic center. This turbulence provides pressure support that counteracts gravity, preventing cloud collapse, except in the densest regions. The broader galactic center region, extending to about 3,000 light-years from the core, transitions gradually into the galactic bar. This elongated structure of stars and gas rotates as a unit and channels material toward the center. The interaction between the bar and the central regions likely plays an important role in supplying gas to the galactic center and influencing its dynamics. The entire galactic center region is permeated by magnetic fields that are stronger and more ordered than those in the disk. These fields form filamentary structures that can be observed in radio waves, some extending hundreds of light-years perpendicular to the galactic plane. The origin of these fields and their role in the ecology of the galactic center remain active areas of research. Another distinctive feature of the galactic center is the presence of numerous supernova remnants, the expanding shells of gas and energy left behind when massive stars explode. These remnants indicate that supernovae occur frequently in this region, perhaps once every 1,000 years compared to once every 100,000 years in our local neighborhood. These frequent supernovae may contribute to another mysterious feature of the galactic center, the diffuse X-ray emission observed throughout the region. This glow indicates the presence of gas heated to millions of degrees, much hotter than typical interstellar gas. The energy from supernovae, along with the activity of the central black hole and the collective effects of stellar winds, likely all contribute to heating this gas. From our location within the galaxy's disk, about 27,000 light-years from the center, we cannot directly observe these wonders in visible light. The same dust that makes the beautiful dark lanes in photographs of the Milky Way also obscures our view of the galactic center at optical wavelengths. It requires a reduction in brightness by a factor of 1 trillion, meaning that for every trillion photons of visible light emitted at the galactic center, only one makes it to Earth. Fortunately, this dust is more transparent to other forms of light. Infrared radiation, with its longer wavelengths, can penetrate the dust much more effectively. Radio waves pass through almost unimpeded. X-rays and gamma rays, with their high energies, can also reach us from the galactic center. By combining observations across these different portions of the electromagnetic spectrum, astronomers have pieced together our current understanding of this hidden realm. What emerges from these studies is a picture of the galactic center as a region of extraordinary extremes. Extremes of density, with stars and gas packed more tightly than anywhere else in the galaxy. Extremes of energy, from the powerful magnetic fields to the hot X-ray emitting gas. Extremes of gravity, in the vicinity of the supermassive black hole, and extremes of star formation, with clusters of massive stars igniting amidst turbulent molecular clouds. Understanding the galactic center is not merely an exercise in astronomical curiosity. The processes occurring there, particularly the relationship between the supermassive black hole and its surroundings, are common throughout the universe. Nearly all large galaxies appear to host central black holes, and the evolution of these black holes is intimately tied to the evolution of their host galaxies. By studying the center of the Milky Way, the only galactic core we can observe in detail, we gain insights into fundamental processes shaping galaxies across cosmic time. The galactic center also serves as a unique laboratory for testing fundamental physics. The extreme gravity near Sagittarius A star allows for tests of general relativity under conditions impossible to replicate on Earth. The dense star cluster provides opportunities to observe rare phenomena, from stellar collisions to tidal disruption events. And the unique chemistry of the molecular clouds offers insights into the formation of complex molecules that may be relevant to the origins of life. For all its extraordinary features, the center of the Milky Way remains in many ways mysterious. New telescopes and observational techniques continue to reveal unexpected structures and phenomena. Theoretical models struggle to fully explain the complex interplay of forces shaping this region, and fundamental questions remain about how the central black hole formed, how the nuclear star cluster assembled, and how the flow of matter and energy between the center and the broader galaxy influences galactic evolution. As our understanding deepens, so too does our appreciation for this remarkable region at the heart of our galactic home. The galactic center stands as a monument to the creative and destructive forces that shape the universe, a place where matter and energy dance in patterns of extraordinary complexity and beauty. At the heart of the galaxy, something ancient still sleeps and stirs. Beyond the luminous spiral arms and bright central bulge of the Milky Way lies a vast, nearly spherical region known as the galactic halo. Unlike the flattened disk where our sun resides, the halo extends in all directions around the galaxy, encompassing a volume hundreds of thousands of light-years in diameter. This region, sparsely populated with stars yet dominant in mass, holds many of the secrets to our galaxy's formation, evolution, and ultimate nature. The halo is composed of several distinct but interrelated components. First, there is a stellar halo, a diffuse population of ancient stars orbiting the galactic center on paths that take them far above and below the disk. Then, there are globular clusters, dense collections of hundreds of thousands of stars that move together through the halo. Surrounding all of this visible matter is an even larger and more massive dark matter halo, an invisible substance detectable only through its gravitational effects. Let us begin our exploration with the stellar halo, the most readily observable component. Unlike the disk, where stars move in orderly, nearly circular orbits around the galactic center, the stars of the halo travel on highly elliptical or even nearly radial paths. These orbits can take them from the dense inner regions of the galaxy out to distances of 100,000 light-years or more. Some halo stars even reach the farthest extremities of the Milky Way, where our galaxy's gravitational influence gradually gives way to the vast emptiness of intergalactic space. The stars of the halo are distinct from those in the disk not only in their orbits, but also in their properties. Halo stars are almost exclusively old, typically more than 10 billion years in age. They formed during the earliest epochs of our galaxy's history, long before the disk had fully developed. This advanced age is reflected in their chemical composition. Halo stars are poor in what astronomers call metals, elements heavier than hydrogen and helium. This low metallicity indicates that they formed from gas that had experienced little prior enrichment from the nuclear fusion processes in stars and supernovae. The ancient metal-poor nature of halo stars makes them invaluable fossils for understanding the Milky Way's early history. By studying their compositions in detail, astronomers can deduce the conditions present during the galaxy's infancy. The most metal-poor stars in the halo may even preserve a record of the very first stars that ever formed in the universe, the so-called population 3 stars that left their chemical imprint on the gas from which these ancient halo stars later condensed. But the stellar halo tells an even more complex story. Careful study of the motions and chemical compositions of halo stars reveals that many of them did not form within the Milky Way at all. Instead, they originated in smaller dwarf galaxies that were later consumed by our galaxy. These stars retain a memory of their birth systems in their collective motions and distinctive chemical patterns. By identifying groups of stars that likely came from the same accreted dwarf galaxy, astronomers can reconstruct the Milky Way's history of galactic cannibalism. The Gaia Space Telescope has revolutionized our understanding of the stellar halo by measuring the positions and motions of billions of stars with unprecedented precision. This wealth of data has revealed that a significant fraction of the halo was built up through mergers, with as much as half of the halo stars originating in other galaxies. The largest contributor was a galaxy astronomers call Gaia Enceladus, or the Gaia sausage, which merged with the Milky Way about 10 billion years ago. But many other accreted systems have been identified as well, from large contributors like the Sagittarius Dwarf galaxy to smaller systems that added just a few million stars to our galaxy. These accretion events did not just bring in individual stars, but also contributed entire star clusters. This brings us to the second major component of the visible halo, globular clusters. These remarkable objects are among the oldest structures in the universe, with most dating back more than 12 billion years. Each globular cluster contains hundreds of thousands or even millions of stars, all born at roughly the same time from the same cloud of gas. The Milky Way hosts about 150 known globular clusters, most of them orbiting within the halo. These clusters are distributed in a roughly spherical pattern around the galactic center, though with a higher concentration toward the center and the disk plane. Their orbits, like those of individual halo stars, can be quite elongated and inclined at various angles to the disk. Globular clusters serve as invaluable time capsules from the early universe, since all the stars in a given cluster formed at about the same time from the same material. Differences in how these stars have evolved are primarily due to differences in their masses. This makes globular clusters excellent laboratories for testing theories of stellar evolution. By comparing the colors and brightnesses of stars in a cluster, astronomers can determine its age with remarkable precision. These age determinations confirm that globular clusters are indeed ancient, with most forming within the first few billion years after the Big Bang. Their chemical compositions are similarly revealing. Like individual halo stars, most globular clusters are poor in heavy elements, though there is a significant range in metallicity among the cluster population. This range in metallicities, along with differences in orbital properties, suggests that not all globular clusters share the same origin. Some likely formed within the early Milky Way itself, but others appear to have been captured from satellite galaxies during mergers. By grouping clusters with similar properties, astronomers can associate them with specific accretion events, further illuminating the Milky Way's assembly history. One of the most remarkable aspects of globular clusters is their longevity. Despite being subjected to various disruptive forces over billions of years, from internal dynamical evolution to tidal stripping by the Milky Way's gravity, many clusters have survived largely intact from the earliest epochs of galaxy formation to the present day. This resilience makes them living fossils, preserving information about conditions in the young universe that would otherwise be lost to time. As we move beyond the visible components of the halo, we encounter one of the greatest mysteries in modern astronomy, dark matter. This invisible substance, detectable only through its gravitational effects, forms a vast halo extending far beyond the visible boundaries of the Milky Way. Indeed, the dark matter halo is the most massive component of our galaxy, outweighing all the stars, gas, dust, and other visible matter combined. The evidence for dark matter in the Milky Way and other galaxies comes primarily from their rotation curves. If we measure how far stars and gas orbit at different distances from the galactic center, we find that the orbital speeds do not decrease with distance as would be expected if only the visible matter were present. Instead, rotation speeds remain high even in the outer regions of the galaxy, indicating the presence of substantial mass that we cannot see. Additional evidence comes from the motions of globular clusters and satellite galaxies orbiting far from the Milky Way's center, the gravitational lensing of background light by the galaxy's mass, and the overall dynamics of stars in the galactic disk and halo. All of these observations point to the same conclusion. There is far more mass in the Milky Way than can be accounted for by the visible components alone. The nature of this dark matter remains one of the most profound open questions in physics. It does not interact with light or other electromagnetic radiation, making it invisible to our telescopes. It appears to interact only weakly, if at all, with normal matter except through gravity. And it must be fundamentally different from the protons, neutrons, and electrons that make up the visible universe. Various theoretical candidates have been proposed for dark matter, from exotic elementary particles produced in the early universe to modifications of our understanding of gravity on galactic scales. The most widely accepted models involve weakly interacting massive particles, or WIMPs, hypothetical particles that interact through gravity and the weak nuclear force, but not through electromagnetism or the strong nuclear force. However, despite decades of experimental searches, no direct detection of these particles has been confirmed. Whatever its nature, dark matter has played a crucial role in shaping the Milky Way's formation and evolution. In the early universe, dark matter began to clump together under its own gravity before normal matter could do the same, forming a gravitational scaffold into which gas could later fall. The largest of these dark matter concentrations became the seeds around which galaxies like the Milky Way would form. As smaller dark matter halos merged with larger ones, they brought along their associated gas and stars, driving the hierarchical assembly of galaxies. This process continues today, as the Milky Way's dark matter halo absorbs the halos of infalling satellite galaxies. The entire cosmic web, the vast network of filaments and voids that defines the largest structures in the universe, is primarily composed of dark matter, with visible galaxies merely tracing its underlying distribution. The shape and extent of the Milky Way's dark matter halo remain subjects of ongoing research. Unlike the visible disk, which is clearly flattened, the dark matter halo is thought to be roughly spherical or perhaps slightly flattened. It extends far beyond the visible boundaries of the galaxy, perhaps to distances of 300,000 light-years or more from the galactic center. Within this vast halo, the density of dark matter decreases with distance from the center, but not as rapidly as the density of stars. In the solar neighborhood, dark matter is present but greatly diluted, with perhaps only a few hundred grams in a volume the size of the Earth. Near the galactic center, the density is much higher, though still small compared to ordinary matter in that region. In the outer reaches of the halo, dark matter completely dominates, outweighing visible matter by factors of hundreds or thousands. The total mass of the Milky Way's dark matter halo is estimated to be around 1 to 2 trillion times the mass of the Sun, compared to about 100 billion solar masses for all the stars in the galaxy. This makes dark matter the dominant component in terms of mass, accounting for about 85% of the Milky Way's total. Despite its overwhelming mass contribution, dark matter's influence on individual stars and planetary systems like our own is minimal. The solar system's dynamics are completely dominated by the Sun's gravity, with dark matter playing essentially no role. Even the Sun's orbit around the galaxy is primarily determined by the combined gravity of other stars and gas, rather than by dark matter directly. It is only on the larger scales of the galaxy as a whole that dark matter's gravitational influence becomes the primary factor shaping structure and motion. The relationship between the visible and dark components of the Milky Way's halo tells us much about how galaxies form and evolve. The visible stellar halo, with its ancient stars and globular clusters, preserves a record of the galaxy's earliest days and subsequent merger history. The dark matter halo, meanwhile, reveals the underlying gravitational potential that has guided this evolution and continues to shape the galaxy's future. Together, these components form a complex, interrelated system. The dark matter halo's gravity holds the entire galaxy together, from the central bulge to the outermost reaches of the stellar halo. Without it, the stars of the Milky Way would fly apart, unable to maintain their orbits around the galactic center. The visible halo, meanwhile, provides our only window into this invisible component, its stars serving as traces of the gravitational field generated by the combined mass of visible and dark matter. Recent research has revealed additional complexity in the structure of both the stellar and dark matter halos. Rather than being smooth and uniform, these components show substantial substructure. The stellar halo contains streams, shells, and other features created by the tidal disruption of accreted dwarf galaxies and star clusters. The dark matter halo is similarly thought to contain numerous subhalos, remnants of the dark matter halos of consumed satellite galaxies that have not yet fully mixed with the main halo. These substructures are not merely curiosities, but provide vital clues about the assembly history of the Milky Way and the nature of dark matter itself. The abundant sizes and internal structures of dark matter subhalos depend on the properties of the dark matter particles, offering a potential way to distinguish between different theoretical models. Similarly, the detailed properties of stellar streams can reveal the shape and lumpiness of the overall gravitational potential, providing indirect information about the distribution of dark matter. As our observations of the Milky Way's halo become more detailed and our theoretical models more sophisticated, we continue to refine our understanding of this vast region and its role in our galaxy's past, present, and future. New surveys are mapping the stellar halo with unprecedented detail, revealing ever more subtle substructures and associations. Advanced computer simulations are modeling the co-evolution of dark and visible matter from the early universe to the present day, helping to interpret these observations in the context of galaxy formation theory. One particularly intriguing aspect of the Milky Way's halo is how it connects our galaxy to the larger cosmic environment. The halo does not end abruptly, but gradually fades into the intergalactic medium. Matter flows both inward and outward across this boundary, with gas falling into the galaxy's gravitational well, while energetic outflows from supernova explosions and the central black hole push material outward. This exchange of matter links the Milky Way to the cosmic web, the vast network of filaments and voids that defines the large-scale structure of the universe. Our galaxy sits within a filament of this web, a region of higher than average density that channels gas toward us and other nearby galaxies. The dark matter halo extends far enough to interact directly with this larger structure, its outer regions merging with the filamentary distribution of dark matter that spans millions of light years. The Milky Way's halo also connects us to other galaxies in our local cosmic neighborhood. Our galaxy and its nearest large neighbor, Andromeda, each have extensive halos that may already be interacting, even though the visible portions of the galaxies remain over 2 million light-years apart. The eventual collision between these galaxies, expected to begin in about 4.5 billion years, will first involve the mixing of their outer halos before the visible components come into contact. On smaller scales, the Milky Way's halo already encompasses numerous satellite galaxies, from the relatively large Magellanic Clouds to tiny dwarf spheroidals containing just a few 100,000 stars. These satellites orbit within our galaxy's dark matter halo, their own smaller halos gradually being stripped away by tidal forces. This ongoing accretion of satellite galaxies continues the process of hierarchical assembly that has built the Milky Way since its earliest days. The stellar halo also contains some of the most extreme and unusual stars in our galaxy. Some halo stars move at such high velocities that they may escape the Milky Way entirely, becoming intergalactic wanderers. Others show chemical compositions so unusual that they may preserve the signature of just one or a few supernovae from the earliest generations of stars. A few rare halo stars even appear to have originated in other galaxies within our local group, flung toward the Milky Way during close encounters between these galaxies, and later captured by our galaxy's gravity. Among the most remarkable objects in the halo are the hypervelocity stars, which travel at speeds exceeding 1 million kilometers per hour relative to the galaxy. These stars were likely once members of binary systems that ventured too close to the supermassive black hole at the galactic center. In such encounters, one star can be captured by the black hole, while the other is flung outward at tremendous speed, a cosmic slingshot effect that launches stars on trajectories that will eventually carry them beyond the Milky Way's gravitational grasp. The halo is also home to some of the oldest planetary systems in the galaxy. While planets around halo stars are challenging to detect due to the star's distance and faintness, those that have been found offer a glimpse of planetary formation under very different conditions than those that created our solar system. These planets form from material much poorer in heavy elements, yet they still manage to coalesce into worlds not entirely unlike those in our solar system. Their existence suggests that planet formation is a robust process that can occur even in environments quite different from the one that produced Earth. As we contemplate the vast, mostly invisible halo that surrounds our galaxy, we are reminded of how much of the universe remains hidden from our direct perception. The stars we see with our eyes, or even with our most powerful telescopes, represent just a small fraction of the matter that shapes cosmic structure and evolution. The dark matter that dominates the mass of the Milky Way's halo, whatever its fundamental nature proves to be, is as essential to our galaxy's existence as the shining stars and swirling gas clouds that capture our imagination. The study of the Milky Way's halo thus takes us to the frontier of human knowledge, where astronomy, physics, and cosmology converge to address some of the most profound questions about the nature of the universe. How did galaxies like ours form and evolve? What is the mysterious dark matter that appears to dominate cosmic structure? How do visible and invisible components interact to create the complexity we observe? As we continue our journey through the Milky Way's history, from its earliest beginnings to its current majesty and onward to its distant future, the halo remains a crucial chapter in this cosmic story. It preserves the ancient past, dominates the invisible present, and will guide the galaxy's evolution far into the future. Beyond the light, a hidden structure holds everything together. The Milky Way does not journey through the cosmos alone. Like a majestic ship sailing the celestial seas, our galaxy is accompanied by a fleet of smaller companions, satellite galaxies bound to us by gravity's invisible tether. These diminutive neighbors, ranging from modest star cities with billions of suns to tiny dwarfs containing just a few 100,000 stars, form an extended family that orbits our galaxy, interacts with it, and in many cases, will eventually merge with it. Most prominent among these companions are the large and small Magellanic Clouds, visible to the naked eye from the southern hemisphere as two misty patches against the night sky. First documented by Persian astronomers nearly 1,000 years ago, these cosmic clouds received their current name from Ferdinand Magellan's crew, who noted them during their historic circumnavigation of Earth in the early 16th century. For the indigenous peoples of the southern continents, these celestial landmarks had been familiar features of the night sky for thousands of years, woven into their myths and used for navigation. The Large Magellanic Cloud, abbreviated as the LMC, is the more substantial of the pair, spanning about 14,000 light-years in diameter and containing approximately 30 billion stars. Located about 160,000 light-years from the Milky Way, it is our galaxy's third largest satellite, after the Sagittarius Dwarf spheroidal galaxy. If the Large Magellanic Cloud existed in isolation, astronomers would classify it as a dwarf irregular galaxy, smaller and less structured than grand spirals like the Milky Way, but still actively forming stars and evolving. The Small Magellanic Cloud, or SMC, is more modest in scale, measuring about 7,000 light-years across and holding perhaps 3 billion stars. It lies slightly farther from us than its larger sibling, at a distance of about 200,000 light-years. Like the large cloud, it shows an irregular structure, lacking the organized spiral arms or smooth elliptical shape of larger galaxies. Both Magellanic Clouds are rich in gas and dust, the raw materials for star formation, and both show evidence of ongoing stellar birth. What makes the Magellanic Clouds particularly fascinating to astronomers is not just their proximity, which allows for detailed observation, but the clear evidence of their interaction with each other and with the Milky Way. Stretching between and beyond these galaxies is the Magellanic Stream, a vast ribbon of gas extending more than 100,000 light-years across space. This stream, composed primarily of hydrogen torn from the Magellanic Clouds, bears witness to the tidal forces exerted by our galaxy's gravitational pull. Recent studies suggest a complex orbital history for the Magellanic Clouds. Rather than having orbited the Milky Way for billions of years as once thought, these galaxies may be on their first close approach to our galaxy. They appear to be traveling together as a bound pair, with the smaller SMC orbiting the larger LMC. As they move through the outer reaches of the Milky Way's dark matter halo, they experience tidal forces that distort their shapes and strip away gas, creating the observed stream. This encounter is not merely a passive one. The Magellanic Clouds are not simply being affected by the Milky Way. They are also influencing our galaxy in return. Their combined gravitational pull may have induced a slight warp in the Milky Way's disk. The gas they contribute to the galactic halo provides fresh fuel for star formation, and their eventual fate, to be fully absorbed by the Milky Way in the distant future, will add to our galaxy's mass and complexity. The Magellanic Clouds themselves show signs of their mutual interaction. A bridge of gas and stars connects the two galaxies, evidence of material drawn out by their gravitational attraction to each other. The Small Magellanic Cloud in particular appears to have been significantly distorted by interactions with its larger companion, with some parts of the SMC stretched toward the LMC by tidal forces. Within both Magellanic Clouds, astronomers observe vibrant stellar nurseries where new stars are being born. The most spectacular of these is the Tarantula Nebula in the Large Magellanic Cloud, one of the largest and most active star-forming regions in the entire local group of galaxies. This enormous complex of gas and young stars spans over 1,000 light-years and would be visible from Earth even if it were located in the Andromeda Galaxy, more than 10 times farther away than its actual position. The proximity of the Magellanic Clouds allows astronomers to study phenomena that would be difficult or impossible to observe in more distant galaxies. Individual stars can be resolved and monitored, revealing details about stellar evolution under conditions different from those in the Milky Way. Supernova explosions in the Magellanic Clouds have provided crucial insights into these cosmic cataclysms, including the renowned supernova 1987A in the Large Magellanic Cloud, the closest observed supernova since the invention of the telescope. Beyond the Magellanic Clouds, the Milky Way hosts a diverse array of smaller satellite galaxies. Most of these are classified as dwarf spheroidals, small rounded collections of ancient stars with little or no ongoing star formation. Unlike the gas-rich star-forming Magellanic Clouds, these dwarf spheroidals are gas-poor and contain primarily old stellar populations. They represent a different class of satellite galaxy, one that has been more thoroughly transformed by interactions with the Milky Way. The closest of these dwarf galaxies is the Sagittarius dwarf spheroidal, discovered only in 1994, despite being just 78,000 light-years from Earth. This proximity to the Milky Way is no coincidence. The Sagittarius dwarf is in the process of being torn apart by our galaxy's tidal forces. It is currently passing through the disk of the Milky Way, with stars stripped from it forming a long stream that wraps around our galaxy multiple times. In a few billion years, the Sagittarius dwarf will be completely absorbed, its identity erased as its stars are fully incorporated into the Milky Way. Other notable satellite galaxies include the Sculptor dwarf, the Fornax dwarf, and the Carina dwarf, each named for the constellation in which it appears from our perspective. These galaxies orbit at distances ranging from about 300,000 to about 500,000 light-years from the Milky Way. Each contains millions to tens of millions of stars, primarily old, low-mass stars that formed billions of years ago. Even smaller are galaxies like the Draco dwarf and the Ursa Minor dwarf, which contain just a few 100,000 stars each. These ultra-faint dwarf galaxies are challenging to detect due to their low luminosity, and many have been discovered only in recent years through systematic sky surveys. Astronomers suspect that many more such galaxies remain undiscovered, hidden by their faintness and the obscuring effects of dust in the Milky Way's disk. What makes these diminutive galaxies particularly intriguing is the role they play in our understanding of dark matter. Observations of the motions of stars within dwarf spheroidal galaxies indicate that they contain far more mass than can be accounted for by their visible stars alone. Indeed, these small galaxies appear to be among the most dark matter-dominated structures in the universe, with dark matter outweighing visible matter by factors of tens or even hundreds to one. This extreme dark matter content makes dwarf spheroidals valuable laboratories for testing theories of dark matter and galaxy formation. Their abundance, distribution, and internal properties can be compared with predictions from different theoretical models, potentially helping to narrow down the nature of the mysterious dark matter that pervades the cosmos. The satellite galaxies of the Milky Way are not distributed randomly in space, but show a peculiar arrangement. Many of them appear to lie in a relatively flat plane around our galaxy, rather than in the spherical distribution that might be expected if they had independent origins. This plane of satellites remains somewhat mysterious, with some astronomers suggesting it indicates a common origin for many of these dwarf galaxies, perhaps as fragments from a larger system that was disrupted in the past. The relationship between the Milky Way and its satellites is dynamic and evolving. As these smaller galaxies orbit our own, they experience various transforming influences. Tidal forces from the Milky Way's gravity can strip away stars and gas. The pressure of the hot gas in the Milky Way's halo can sweep away the interstellar medium of satellites as they move through it, a process called ram pressure stripping. And close passages through the disk of the Milky Way can trigger bursts of star formation or disrupt the structure of satellite galaxies. Over time, these processes tend to transform gas-rich, star-forming dwarf irregular galaxies like the Magellanic Clouds into gas-poor, quiescent dwarf spheroidals. The longer a satellite has orbited the Milky Way, the more thoroughly it tends to be transformed. This evolutionary sequence helps explain the diverse properties observed among the satellite population, from the still active Magellanic Clouds to the ancient, gas-free dwarf spheroidals that have orbited our galaxy for many billions of years. The ultimate fate of most satellite galaxies is to be fully absorbed by the Milky Way. This process of galactic cannibalism, where larger galaxies consume smaller ones, has been a fundamental aspect of galaxy evolution throughout cosmic history. The stellar halo of the Milky Way, with its ancient stars on highly elongated orbits, is thought to be comprised largely of the remains of satellite galaxies accreted over billions of years. Evidence for this ongoing accretion can be seen in the numerous stellar streams that thread through the Milky Way's halo. These streams, like the one associated with the Sagittarius Dwarf, are the tidally stretched remains of satellites being torn apart by our galaxy's gravitational pull. By identifying and mapping these streams, astronomers can reconstruct much of the Milky Way's accretion history, determining which satellites have been consumed and when these mergers occurred. Not all satellite galaxies will share this fate, however. Some orbit the Milky Way at such large distances that they may never be fully absorbed. Others may eventually be lost to our galaxy if they receive a gravitational boost that increases their orbital energy, perhaps during the future merger between the Milky Way and Andromeda. The complex dance of galaxies in our local cosmic neighborhood ensures that the population of satellites will continue to evolve over billions of years. The study of the Milky Way's satellites connects to broader questions in cosmology and galaxy formation. The standard model of cosmology, called lambda CDM, predicts that dark matter should form a hierarchy of structures, from massive halos hosting galaxies like the Milky Way down to much smaller subhalos. Various solutions to this problem have been proposed. Perhaps many dark matter subhalos fail to form or retain stars, remaining invisible to our telescopes. Perhaps the processes that transform satellites over time have rendered some too faint to detect with current technology. Or perhaps the properties of dark matter itself differ from those assumed in the standard model, suppressing the formation of small-scale structure. Ongoing surveys continue to discover new satellite galaxies around the Milky Way, gradually increasing the known population. Each new discovery adds to our understanding of the complex ecosystem of galaxies in our local cosmic neighborhood and helps to refine our models of how galaxies form and evolve in a universe dominated by dark matter. As we observe the Magellanic Clouds and other satellite galaxies orbiting the Milky Way, we are witnessing a process that has been central to our galaxy's growth throughout its history. The current satellites represent the latest wave of a continuing flow of smaller galaxies being drawn into the Milky Way's gravitational embrace. Some are falling in for the first time, like the Magellanic Clouds. Others are in the final stages of disruption after orbiting our galaxy for billions of years. Together, these satellites and the streams of stars left by those already absorbed form a complex, evolving system that extends the Milky Way's influence far beyond the visible disk. Our galaxy's gravitational reach extends to distances of at least 1 million light-years, encompassing a volume of space in which dozens of smaller galaxies move along their various orbits, some destined to merge with us, others perhaps to orbit indefinitely in the distant outskirts of our galactic system. Smaller galaxies drift in our orbit, some destined to join us, others to drift forever. Among the hundreds of billions of stars that make up the Milky Way, one ordinary yellow dwarf star, our Sun, orbits in the quiet suburbs of the galactic disk. Around this unremarkable star circles a small blue world, the third planet from the Sun, Earth, our home. To understand our place in the galaxy is to understand both our cosmic location and our relationship to the vast stellar city that surrounds us. The Sun is located approximately 27,000 light-years from the galactic center, a little more than halfway from the center to the edge of the stellar disk. This places us in what astronomers call the Orion Arm or Orion Spur, a minor spiral feature that lies between two major spiral arms, the Sagittarius Arm toward the galactic center and the Perseus Arm toward the outer galaxy. Our position within the Milky Way places us in a remarkably ordinary location. We are neither in the densely packed central regions nor in the sparse outer fringes. The stellar density in our neighborhood is about 1 star per cubic parsec, or 1 star in a cube about 3.3 light-years on each side. This density is typical for the mid-regions of the galactic disk, neither crowded nor empty. The Sun orbits the center of the galaxy at a speed of about 230 kilometers per second. At this velocity, it takes the Sun approximately 230 million years to complete one circuit around the galaxy, a period sometimes referred to as a cosmic year or galactic year. Since the Sun formed about 4.5 billion years ago, it has completed about 20 galactic orbits, a cosmic journey that has carried it about 600 billion kilometers through space. This orbital motion is not perfectly circular. Like most stars in the disk, the Sun follows an elliptical path that oscillates slightly closer to, and then farther from, the galactic center. It also bobs up and down through the mid-plane of the galactic disk, crossing it about every 30 million years. These subtle variations in the Sun's orbit reflect the complex gravitational influence of the rest of the galaxy. The Sun does not travel alone on its journey around the Milky Way. It carries with it the entire solar system, the planets, moons, asteroids, and comets that orbit our star, all moving as a unit through the galaxy. The planets maintain their much smaller orbits around the Sun as the entire system glides through the interstellar medium, the tenuous gas and dust that fills the space between stars. Our position in the galaxy's disk places us in a relatively flat plane. If we look in the plane of the Milky Way, we see the band of light that gives our galaxy its name, the combined glow of billions of distant stars too far away to be seen individually. If we look perpendicular to the plane, above or below the disk, we see far fewer stars, as the disk is quite thin compared to its diameter. From our location embedded within it, we cannot see the overall spiral structure of the Milky Way. The dust in the galactic plane obscures our view of distant regions, particularly toward the galactic center. It is only by observing at wavelengths that can penetrate this dust, such as radio and infrared, and by carefully mapping the positions and motions of stars and gas, that astronomers have been able to determine our galaxy's overall shape and our position within it. One of the most remarkable aspects of our galactic location is how well suited it is for life as we know it. The inner regions of the galaxy, while rich in the heavy elements needed for rocky planets, are also more crowded with stars. The greater stellar density increases the risk of gravitational disturbances to planetary systems and of nearby supernova explosions that could damage developing biospheres. The outer regions, while less crowded, have fewer heavy elements, potentially making the formation of rocky planets like Earth less common. Our intermediate position represents a kind of Goldilocks zone within the galaxy, neither too crowded nor too sparse, neither too metal-rich nor too metal-poor. This fortuitous placement may be one of the factors that allowed life to develop and flourish on Earth over billions of years. Another important aspect of our galactic location is our distance from the center. The central regions of the Milky Way are more active and energetic than our quiet neighborhood. The supermassive black hole at the galactic center, while currently relatively quiet, has been more active in the past and may become so again in the future. Intense radiation from this activity and from the dense concentration of stars near the center could pose challenges for life. Our comfortable distance from these energetic regions provides a more stable environment. The specific properties of the Orion Arm, where we reside, may also be significant. Unlike the major spiral arms, which contain many massive stars that live short lives and die in supernova explosions, the Orion Spur is a relatively quiet stellar neighborhood. It contains a mix of stars of different masses and ages, but without the concentration of massive, short-lived stars found in the main spiral arms. This location provides a balance between too much and too little stellar activity. Massive stars and their supernovae are important for enriching the interstellar medium with heavy elements needed for rocky planets and life. But too many nearby supernovae could be hazardous. Our position in a minor spiral feature gives us access to the elements produced by past generations of massive stars without exposing us to excessive radiation and disturbance. The Sun's particular orbit around the galaxy also appears favorable for life. Its nearly circular path keeps it at roughly the same distance from the galactic center, avoiding excursions into regions with different conditions. The Sun's orbit also stays close to the galactic plane without venturing too far above or below it, keeping us in the thin disk where most of the galaxy's stars and gas reside. As the Sun moves through the galaxy, it occasionally passes through regions of slightly higher density, such as spiral arms or smaller gas clouds. These passages might alter the influx of cosmic rays reaching the solar system or affect the orbits of distant comets in the Oort Cloud, potentially changing the rate of comet impacts on Earth. Some researchers have suggested that these passages might correlate with mass extinction events in Earth's history, though this remains speculative. Beyond our immediate stellar neighborhood, the Sun's nearest large neighbors are star systems like Alpha Centauri, a triple system about 4.3 light-years away, and Sirius, a binary system about 8.6 light-years distant. These and other nearby stars form a local stellar neighborhood that moves through the galaxy together, though with small differences in velocity that will gradually change our relative positions over millions of years. The Sun and its neighbors are currently passing through a region called the local bubble, a relatively empty cavity in the interstellar medium about 300 light-years across. This bubble was likely created by supernova explosions within the last 10 to 20 million years, which swept out much of the gas and dust that would normally fill this volume of space. The lower density of the interstellar medium within this bubble means that the solar system encounters less material as it moves through space. On even larger scales, our Milky Way galaxy is part of a collection of galaxies called the Local Group. This gravitationally bound cluster includes the Andromeda Galaxy, which is slightly larger than the Milky Way, the Triangulum Galaxy, which is smaller, and dozens of dwarf galaxies, including the Magellanic Clouds discussed in the previous chapter. The Local Group spans about 10 million light-years and is moving together through space. The Local Group, in turn, is part of the Virgo supercluster, a vast collection of galaxy groups and clusters spanning about 110 million light-years. This supercluster, along with others nearby, is being drawn toward an enormous concentration of mass called the Great Attractor, creating a flow of galaxies through the cosmos. From our perspective on Earth, these vast cosmic structures are invisible to the naked eye. What we see when we look up at the night sky depends greatly on our location on Earth and the conditions of viewing. From urban areas, light pollution obscures all but the brightest stars. But from truly dark sites, far from artificial lights, the view can be spectacular. On a clear, moonless night from a dark location, the band of the Milky Way stretches across the sky, a hazy river of light representing our edge-on view of the galactic disk. This band is brightest toward the constellation Sagittarius, where we look toward the galactic center. It appears thinner and fainter toward Auriga and Perseus, where we look toward the outer galaxy. The dark patches and rifts within this band are not empty spaces, but rather clouds of dust that obscure the light of distant stars. The individual stars we see with the naked eye are almost all relatively nearby, within about 1,000 light-years of the Sun. These represent just a tiny fraction of the stars in our galaxy, those that happen to be close enough and bright enough to be visible. The vast majority of the Milky Way stars are too distant or too faint to be seen without the aid of telescopes. The constellations, those patterns of stars that cultures around the world have recognized and named, bear no physical relationship to each other. The stars that form these patterns are at widely varying distances from Earth and from each other. Their apparent arrangement is simply a matter of our perspective, a two-dimensional projection of three-dimensional space as seen from our particular vantage point. Yet these patterns have served humanity as guides for navigation, markers of the seasons, and frameworks for stories and myths that connect us to the cosmos. The constellations visible from a given location on Earth change throughout the year as our planet orbits the Sun, creating the cycle of seasonal skies that has been observed and recorded by cultures throughout human history. Our ability to observe and understand our place in the galaxy has evolved dramatically over time. Ancient civilizations could see the Milky Way and the brighter stars, but had no way to measure their distances or understand their true nature. The invention of the telescope in the early 17th century began to reveal the vastness of the cosmos, showing that the hazy band of the Milky Way was composed of countless individual stars. But it was not until the early 20th century that astronomers definitively established that the Milky Way is a galaxy, a vast island of stars, and that our Sun is just one of billions within it. The work of astronomers like Harlow Shapley and Edwin Hubble revolutionized our understanding of the scale of the universe and our place within it. Today, advanced telescopes observing across the electromagnetic spectrum, from radio waves to gamma rays, continue to refine our understanding of the Milky Way's structure and our location within it. Space missions like Gaia are mapping the positions and motions of billions of stars with unprecedented precision, creating the most detailed three-dimensional map of our galaxy ever constructed. This scientific understanding of our cosmic address, from Earth to the solar system to our location in the Milky Way and beyond, represents one of humanity's greatest intellectual achievements. It places us in context, revealing our planet as one small world in a vast cosmic ocean, a perspective that both humbles us and expands our horizons. Yet for all this scientific progress, there remains something deeply moving about the simple act of looking up at the night sky, seeing the band of the Milky Way stretching overhead, and knowing that we are looking at our galactic home from the inside. This view connects us to both the most advanced astronomical knowledge and to the earliest human experiences of wondering about the lights in the night sky. Our place in the galaxy, this quiet neighborhood in the Orion Arm, has provided the stable conditions in which life could emerge and evolve on Earth. The heavy elements that make up our world and our bodies were forged in previous generations of stars scattered through the galaxy by supernovae, and eventually incorporated into the cloud of gas and dust that formed our solar system. In this sense, we are not merely observers of the Milky Way, but products of it, our very existence intimately connected to processes that have unfolded over billions of years throughout our galaxy. The iron in our blood, the calcium in our bones, the carbon that forms the basis of life itself, all were created in stellar furnaces and distributed through the galaxy before becoming part of Earth and eventually part of us. As we continue our journey around the galactic center, completing an orbit every 230 million years, we carry with us this understanding of our place in the cosmic context. We are travelers on a small blue world, orbiting an ordinary star in the quiet suburbs of a majestic spiral galaxy, part of a universe of astonishing scale and beauty. In one small swirl of one vast spiral, a pale blue dot turns. Studying our own galaxy presents a unique challenge. Unlike distant galaxies that we can observe in their entirety from the outside, we must map the Milky Way from within, like trying to determine the shape of a vast forest while standing among the trees. This inside-out perspective has required astronomers to develop ingenious methods for piecing together the structure of our galactic home. The history of Milky Way research reflects humanity's evolving understanding of our place in the cosmos. Ancient cultures around the world recognized the band of light stretching across the night sky and incorporated it into their mythologies. The Greek philosopher Democritus, in the 5th century BCE, was among the first to suggest that this misty band might consist of distant stars too faint to be seen individually. This insight would wait nearly 2 millennia for confirmation. It was Galileo Galilei who, in 1610, first turned a telescope toward the Milky Way and confirmed that it indeed consists of countless individual stars. This discovery began the scientific study of our galaxy, though the true nature and scale of the Milky Way remained elusive for centuries more. Even into the early 20th century, astronomers debated whether the Milky Way encompassed the entire universe or was just one of many island universes, what we now call galaxies. This fundamental question was settled in the 1920s when Edwin Hubble used the newly built 100-inch telescope at Mount Wilson Observatory to identify individual stars in the Andromeda Nebula, now known as the Andromeda Galaxy. By observing variable stars, whose intrinsic brightness was known, Hubble could calculate the distance to Andromeda, proving it lay far beyond the bounds of the Milky Way. Our galaxy was revealed to be just one among billions in a vast universe. Around the same time, Harlow Shapley used the distribution of globular clusters to determine that the Sun is not at the center of the Milky Way, as had long been assumed, but rather in the galactic suburbs. By mapping the positions of these clusters, Shapley showed that they form a roughly spherical distribution centered about 27,000 light-years from our position. This marked the beginning of our modern understanding of the Milky Way's structure and our place within it. The challenge of mapping our galaxy from the inside is compounded by the presence of interstellar dust, microscopic solid particles that permeate the space between stars. This dust absorbs and scatters light, particularly at visible wavelengths, creating a cosmic fog that obscures our view of distant regions of the galaxy. The effect is especially pronounced when looking through the plane of the galactic disk, where dust is most concentrated. Toward the galactic center, this extinction reduces the brightness of visible light by a factor of 1 trillion, effectively hiding the heart of our galaxy from optical telescopes. To overcome this limitation, astronomers have turned to other portions of the electromagnetic spectrum. Infrared light, with wavelengths longer than visible light, can penetrate dust clouds more effectively. Radio waves pass through dust almost unimpeded. X-rays and gamma rays, produced by the most energetic phenomena, can also reach us from great distances. By combining observations across multiple wavelengths, astronomers can construct a more complete picture of the Milky Way's structure. Radio astronomy has been particularly valuable for mapping our galaxy's spiral arms. Neutral hydrogen gas, the most abundant element in the universe, emits radio waves at a characteristic wavelength of 21 centimeters. This emission can be detected from across the galaxy, allowing astronomers to trace the distribution of hydrogen gas. Because this gas tends to concentrate in spiral arms, mapping its distribution has helped reveal the Milky Way's spiral structure. The technique of radio spectroscopy adds another dimension to these observations. The 21 centimeter emission line is subtly shifted in frequency due to the Doppler effect, becoming slightly higher in frequency when the gas is moving toward us and slightly lower when moving away. By measuring these shifts, astronomers can determine the velocity of hydrogen gas clouds throughout the galaxy. Combined with a model of galactic rotation, these velocity measurements can be converted into distances, creating a three-dimensional map of hydrogen gas in the Milky Way. Similar techniques can be applied to other molecules found in interstellar space. Carbon monoxide, for example, emits radiation at millimeter wavelengths and serves as a tracer for molecular hydrogen, which is difficult to observe directly. By mapping the distribution of carbon monoxide, astronomers can locate the dense molecular clouds where stars form, revealing the Milky Way's stellar nurseries, and by extension, its spiral arms where star formation is most active. Infrared astronomy has revolutionized our view of the galactic center and inner regions, beginning with balloon-borne and airborne telescopes in the 1960s, and continuing with space-based observatories like the Infrared Astronomical Satellite, the Spitzer Space Telescope, and most recently, the James Webb Space Telescope. Infrared observations have penetrated the dust veil that hides the heart of the Milky Way. These observations revealed the supermassive black hole at the galactic center, Sagittarius. A star, not through direct imaging, which is impossible for a black hole, but by tracking the motions of stars orbiting around it. By observing these stars over many years, astronomers could measure their orbits with extraordinary precision, using them as probes of the gravitational field at the galaxy's core. The orbital data demonstrated conclusively that a mass of about 4 million times that of our Sun is concentrated in a region smaller than our solar system, a finding consistent only with a supermassive black hole. Another breakthrough in our understanding of the Milky Way came from an unexpected direction: the detection of cosmic gamma-ray bubbles extending above and below the galactic center. Discovered by NASA's Fermi Gamma-ray Space Telescope in 2010, these structures, now called the Fermi bubbles, extend about 25,000 light-years perpendicular to the galactic plane. They likely result from a period of intense activity at the galactic center millions of years ago, perhaps when the central black hole was feeding more actively, or when a burst of star formation drove a powerful galactic wind. In the realm of optical astronomy, the challenge of dust extinction has been partially overcome by focusing on specific windows through the galactic plane where dust is less concentrated, and by studying individual stars whose distances can be determined through various techniques. One such technique is stellar parallax, the apparent shift in a star's position when viewed from different points in Earth's orbit around the Sun. This method provides the most direct measurement of stellar distances, but is limited to relatively nearby stars. For more distant stars, astronomers rely on standard candles, objects whose intrinsic brightness is known and can be compared with their apparent brightness to calculate distance. Certain types of variable stars, like Cepheids and RR Lyrae stars, serve as excellent standard candles because the relationship between their pulsation period and luminosity is well established. By identifying these stars throughout the galaxy and measuring their properties, astronomers can map the distribution of stellar populations at different distances. The most comprehensive optical survey of the Milky Way has come from the European Space Agency's Gaia mission, launched in 2013. This space telescope is creating a three-dimensional map of our galaxy by measuring the positions, distances, and motions of more than 1 billion stars with unprecedented precision. By the time it completes its mission, Gaia will have observed each of its target stars about 70 times, tracking their movements across the sky and measuring their parallaxes to determine their distances. The data from Gaia has already transformed our understanding of the Milky Way. It has revealed previously unknown substructures in the disk and halo, traced the wakes left by dwarf galaxies as they pass through the Milky Way, and identified the stellar streams created when satellite galaxies are torn apart by our galaxy's tidal forces. Perhaps most significantly, Gaia has allowed astronomers to track the motions of stars in 3 dimensions, providing a dynamic view of our galaxy, not as a static structure, but as an evolving system. Complementing these observational approaches are theoretical models and computer simulations. By applying our understanding of gravity, gas dynamics, star formation, and other physical processes, astronomers can create simulated galaxies that evolve over billions of years. These simulations can then be compared with observations of the Milky Way and other galaxies to test our understanding of galaxy formation and evolution. Simulations have been particularly valuable for understanding the dark matter halo that surrounds the visible Milky Way. This invisible component cannot be observed directly, but reveals itself through its gravitational effects on stars and gas. By modeling the distribution of dark matter and its influence on visible matter, astronomers can better interpret observations and reconstruct the Milky Way's formation history. Recent years have seen the emergence of galactic archaeology as a powerful approach to studying the Milky Way's history. Just as archaeologists on Earth study artifacts to reconstruct human history, galactic archaeologists examine the chemical compositions, ages, and orbits of stars to piece together our galaxy's past. Each generation of stars leaves a chemical fingerprint in the interstellar medium, enriching it with specific elements created through nuclear fusion and supernova explosions. By measuring the abundances of these elements in stars of different ages, astronomers can trace the chemical evolution of the galaxy over time. Spectroscopy is the key technique for this chemical analysis. When the light from a star is spread into its component wavelengths, specific wavelengths are absorbed by elements in the star's atmosphere, creating a pattern of dark lines in the spectrum. The positions and strengths of these absorption lines reveal which elements are present and in what quantities. Modern spectroscopic surveys can measure the chemical compositions of hundreds of thousands of stars, creating a vast database for galactic archaeology. One of the most ambitious of these surveys is the Sloan Digital Sky Survey's Apogee project, which has measured the spectra of more than 500,000 stars, focusing on the infrared to penetrate the dust in the galactic plane. By combining chemical information from Apogee with positional and kinematic data from Gaia, astronomers can identify groups of stars that likely formed together or came from the same accreted dwarf galaxy, even if those stars are now widely separated in space. These chemical and kinematic studies have revealed that the Milky Way's history has been shaped by multiple significant merger events. The most notable is the Gaia Enceladus, or Gaia sausage merger, which occurred about 10 billion years ago, when a dwarf galaxy containing about 500 million stars collided with the young Milky Way. This collision contributed a substantial fraction of the stars now found in the inner halo, and may have triggered the formation of the thick disk component of our galaxy. Other mergers have been identified through similar techniques, with each leaving its signature in the chemical compositions and orbital properties of stars. By reconstructing this merger history, astronomers can understand how the Milky Way grew over cosmic time, accreting smaller galaxies and their stars, while continuing to form new stars from gas falling into its gravitational well. The interplay between star formation, chemical enrichment, and structural evolution continues to be a focus of Milky Way studies. By measuring the ages of stars in different parts of the galaxy, astronomers have found evidence for inside-out growth, with the inner regions forming stars earlier than the outer regions. The disk appears to have grown gradually in radius over time, while star formation has become increasingly concentrated in the thin disk rather than the thicker component that formed earlier. The spiral structure of the Milky Way remains challenging to map precisely. Unlike external galaxies, where the entire spiral pattern can be seen at once, we must infer our galaxy's spiral arms from limited information. Recent years have seen progress through combined analyses of young stars, star-forming regions, molecular clouds, and neutral hydrogen gas, all of which trace spiral structure. These studies suggest that the Milky Way has 4 major spiral arms, with the Sun located in a minor feature called the Orion Arm, or local spur. Another area of active research is the nature and history of the galactic bulge, the spheroidal collection of stars at the center of the Milky Way. Long thought to be the result of an early period of rapid star formation, the bulge is now understood to be more complex. Part of it appears to be a pseudobulge, formed not through mergers, but through internal processes in the disk, particularly the buckling of the galactic bar. Other components may indeed result from early star formation, or from accreted satellite galaxies. Disentangling these different populations and their origins remains a challenge for Milky Way researchers. The future of Milky Way studies looks bright, with new observatories and surveys planned that will further revolutionize our understanding. The Vera C. Rubin Observatory, under construction in Chile, will conduct the legacy survey of space and time, observing the entire visible sky repeatedly over 10 years to detect variable and moving objects. This will identify vast numbers of RR Lyrae and other variable stars throughout the galaxy, providing additional distance markers for mapping the Milky Way's structure. The Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will combine a Hubble-sized mirror with a wide-field instrument to survey large portions of the sky at infrared wavelengths. This will allow it to peer through the galactic dust and observe stars in the bulge and on the far side of the galaxy, regions that remain poorly mapped. Combined with its precision astrometric capabilities, this will extend our 3-dimensional map of the Milky Way to greater distances than currently possible. Radio astronomy continues to advance as well, with facilities like the Square Kilometre Array, under construction in Australia and South Africa, poised to transform our view of the galaxy at radio wavelengths. This international project will map neutral hydrogen throughout the Milky Way with unprecedented sensitivity and resolution, tracing the galaxy's gaseous component in exquisite detail. As our tools and techniques improve, our understanding of the Milky Way grows ever more sophisticated. From the earliest recognition of the galaxy as a collection of stars to the complex, multifaceted view we have today, the study of our galactic home reflects humanity's expanding cosmic perspective. We now see the Milky Way not as a static backdrop to the night sky, but as a dynamic, evolving system with a rich and complex history written in the stars. Yet for all our progress, much remains unknown. The exact spiral pattern of our galaxy, the detailed distribution of dark matter, the nature of the supermassive black hole at the center, and its influence on galactic evolution, these and many other questions continue to drive research. Each answer often raises new questions, keeping the study of the Milky Way at the forefront of astronomical research. Perhaps the most remarkable aspect of Milky Way studies is that they connect the grandest cosmic scales to our immediate surroundings. The stars we see in the night sky are our neighbors in this vast galactic city. The elements in our bodies were forged in Milky Way stars that lived and died long before our sun formed. And the ongoing processes of star formation, stellar evolution, and galactic dynamics will shape the future of our cosmic home long after our brief lives have ended. To see our home, we must look out in every direction and backward in time. Having explored the past and present of our galactic home, we now turn our gaze toward its future. The Milky Way, like all galaxies, is not a static object, but a dynamic system that continues to evolve. Its future will be shaped by processes already underway, from the gradual consumption of its gas supply to the inevitable collision with our neighboring galaxy, Andromeda. This cosmic forecast, written in the laws of physics and the current state of our local universe, extends billions of years into the future, far beyond the span of human civilization, but well within the lifetime of our galaxy. In the relatively near cosmic future, over the next few 100 million years, the Milky Way will continue on its current evolutionary path. Stars will continue to form in the spiral arms, though at a gradually declining rate as the supply of cold, dense gas is depleted. This star formation will continue to enrich the interstellar medium with heavy elements, increasing the overall metallicity of the galaxy. The disk will continue to grow slowly in radius as gas in the outer regions collapses to form new stars, and as the orbits of some stars migrate outward due to interactions with spiral arms and the central bar. The supermassive black hole at the galactic center, Sagittarius A star, will continue to grow slowly by accreting gas and occasionally consuming stars that venture too close. This growth will be modest, however, as there is relatively little gas flowing toward the galactic center in the current epoch. Occasional more dramatic feeding events might occur if a large gas cloud or even a small satellite galaxy falls toward the center, but these would be temporary departures from an otherwise quiescent state. The Sun itself will continue its steady orbit around the galactic center, completing another circuit every 230 million years. Over the next billion years, it will likely pass through several spiral arms, each passage perhaps affecting Earth's climate as the solar system moves through regions of slightly higher cosmic ray flux. These effects, while potentially significant for life on Earth, would not alter the overall structure or evolution of the galaxy. Looking further ahead to timescales of billions of years, more dramatic changes await our galaxy. The most significant of these is the impending collision with the Andromeda Galaxy, our largest neighboring galaxy. Currently located about 2.5 million light-years from the Milky Way, Andromeda is moving toward us at about 110 kilometers per second. Astronomical measurements indicate that the Milky Way and Andromeda will begin to merge in about 4.5 billion years, roughly the same time that our Sun will exhaust its hydrogen fuel and begin to evolve off the main sequence. This galactic collision will unfold over approximately 2 billion years, a slow-motion cosmic dance that would appear majestic if viewed from outside. The first encounter will distort both galaxies, drawing out long tidal tails of stars and gas. The galaxies will then move apart again, but their mutual gravitational attraction will pull them back for a second encounter. This process may repeat several times before the two galaxies finally merge into a single, larger system. Despite the dramatic nature of this merger, it would pose no direct threat to planetary systems like our own. Galaxies are mostly empty space, with stars typically separated by distances millions of times greater than their diameters. When galaxies collide, the stars within them generally do not. Instead, they follow new orbits determined by the changing gravitational field of the combined system. Some stars may be flung into highly elongated orbits or even ejected from the galaxy entirely, but the vast majority will simply find themselves part of a new, larger galaxy. The gas components of the two galaxies, unlike the stars, will indeed collide. When gas clouds from the Milky Way and Andromeda meet, they will compress and likely trigger an extensive burst of star formation. This starburst phase will be one of the most active periods of star formation in either galaxy's history, giving birth to a new generation of stars from the combined gas of both progenitors. The end result of this merger will be an elliptical galaxy, sometimes whimsically called Milkomeda by astronomers. Unlike the flat, rotating disks of spiral galaxies, elliptical galaxies are more three-dimensional in structure, with stars moving on more random and elongated orbits. The beautiful spiral patterns of both the Milky Way and Andromeda will be destroyed in the merger, replaced by a smoother, more featureless distribution of stars. This transformation from spiral to elliptical is a common evolutionary pathway for galaxies. Spiral galaxies generally have substantial gas supplies and ongoing star formation, while ellipticals tend to be gas-poor, with little new star formation. The collision between the Milky Way and Andromeda will accelerate this transition, using up much of the remaining gas in a final burst of star formation and heating the rest to the point where it can no longer collapse to form new stars. The merger with Andromeda is not the only galactic collision in the Milky Way's future. The Triangulum galaxy, the third largest member of our local group, may also join the merger, creating an even larger elliptical galaxy. Several smaller dwarf galaxies that now orbit the Milky Way and Andromeda will also be absorbed into the merged system. The result will be a giant elliptical galaxy containing most of the mass of the present local group. While these mergers are unfolding, another important process will be quietly transforming our galaxy: the gradual fading of star formation. Galaxies form new stars only as long as they have cold, dense gas available as raw material. In the Milky Way, this gas is steadily being converted into stars, with some replenishment from material falling in from the intergalactic medium. However, the rate of gas consumption exceeds the rate of replenishment, meaning that the gas supply is gradually being depleted. Currently, the Milky Way forms about 1 to 2 solar masses worth of new stars each year, a modest rate compared to its peak activity billions of years ago. Over the next few billion years, this rate will continue to decline as the remaining gas is converted to stars or heated to the point where it cannot collapse. The merger with Andromeda will briefly increase the star formation rate during the starburst phase, but it will also use up or heat much of the remaining gas, ultimately accelerating the decline of star formation. By about 10 billion years from now, with the Milky Way-Andromeda merger complete and most of the gas consumed, star formation will have almost entirely ceased in the resulting elliptical galaxy. New stars will form only very rarely from small pockets of cooling gas released by dying stars. The galaxy will enter a long, quiet period of stellar evolution as its existing stars gradually age and evolve. During this period, the stellar population of the merged galaxy will slowly change in character. Massive stars, which burn their fuel quickly, will die out first, exhausting their nuclear fuel and ending their lives as supernovae or black holes. Intermediate mass stars like our Sun will live longer, typically for about 10 billion years, before swelling into red giants and eventually shedding their outer layers to form planetary nebulae, leaving behind white dwarf stars. The least massive stars, red dwarfs with less than about half the Sun's mass, burn their fuel so slowly that they can shine steadily for trillions of years. As the most massive and luminous stars die out, the galaxy will gradually grow dimmer and redder in color. The bright blue light of young, massive stars will be replaced by the more subdued glow of older, redder stars. After about 10 to 20 billion years, the merged Milky galaxy will have transformed into a red and dead elliptical, a common fate for galaxies that have exhausted their gas supply and ceased forming new stars. The supermassive black holes from the Milky Way and Andromeda will also eventually merge during this period. Initially, they will orbit each other at the center of the combined galaxy, but gradually they will spiral closer together due to a process called dynamical friction, where their motion through the stellar background creates a drag force. When they get very close, they will emit gravitational waves, ripples in space-time that carry away energy and angular momentum, causing the black holes to merge. This event will release an enormous amount of energy in gravitational waves, though it would not be directly visible to any conventional telescope. The merged supermassive black hole, with a mass of perhaps 100 million times that of the Sun, will sit at the center of Milky, occasionally consuming stars that venture too close, but otherwise remaining relatively quiet. It will make up only a tiny fraction of the galaxy's total mass, but will influence the orbits of stars in the central regions through its powerful gravitational field. Looking even further ahead, into the distant cosmic future, tens of billions of years from now, larger-scale changes will affect not just our galaxy, but the entire local universe. The accelerating expansion of the universe, driven by dark energy, will gradually carry distant galaxies beyond our cosmic horizon. Galaxies not bound to our local group will recede faster and faster, eventually becoming impossible to see or interact with. The local group itself, gravitationally bound against the cosmic expansion, will continue to consolidate. The merged Milky galaxy, along with any remaining satellite galaxies, will gradually form an increasingly isolated island in an otherwise empty observable universe, The light from more distant galaxies, stretched by the expanding cosmos, will be redshifted to the point of invisibility. Within this isolated galaxy, stellar evolution will continue its slow, inexorable course. White dwarfs will gradually cool to black dwarfs, their thermal energy radiated away over hundreds of billions of years. Neutron stars will cool even more quickly. Black holes will persist, occasionally capturing passing stars but more often simply existing as massive gravitational wells in the galaxy. The longest-lived stars, red dwarfs, will continue to shine for trillions of years, gradually converting their hydrogen to helium through nuclear fusion. Eventually, even these stars will exhaust their fuel and end their lives, leaving behind white dwarfs that will slowly cool to the background temperature of space. After about 100 trillion years, all normal stellar evolution will have ceased, leaving a galaxy populated primarily by black dwarfs, neutron stars, and black holes. Over even longer timescales of quintillions to decillions of years, exotic processes will continue to transform this dead galaxy. Black holes will very gradually evaporate through Hawking radiation, a quantum process that causes them to lose mass and eventually disappear in a final burst of high-energy particles. The supermassive black hole at the center will be the last to go, persisting for perhaps a Google years, a one followed by 100 zeros. Proton decay, if it occurs as predicted by some theories, would eventually break down the remaining matter in white dwarfs and other remnants, converting it to lighter particles and radiation. In the most extreme far future, even the fabric of space-time itself might decay, ending the universe as we know it, or perhaps giving birth to a new cosmos with different physical laws. These far future scenarios, while fascinating to contemplate, involve timescales so vast that they dwarf not just human history, but the entire current age of the universe. They represent the ultimate fate of matter and energy in a cosmos governed by the laws of physics as we currently understand them. Yet they are subject to revision as our understanding of fundamental physics evolves, particularly in areas like quantum gravity and the ultimate nature of dark energy. For now, we can be more confident about the nearer-term future of our galaxy, particularly its impending merger with Andromeda. This process, while still far in the human future, is close enough in cosmic terms to be predicted with reasonable confidence, based on current observations and well-established physics. The transformation of the Milky Way from a star-forming spiral to part of a larger, quiescent elliptical galaxy represents the next major chapter in our galaxy's long evolutionary history. This transition is part of a broader pattern seen throughout the universe, where galaxies evolve from gas-rich star-forming systems to gas-poor, quiescent ones. Some galaxies make this transition gradually, slowly exhausting their gas supply and ceasing star formation. Others, like the Milky Way, experience more dramatic transformations through mergers with other galaxies. The end result in either case is a red elliptical galaxy, where star formation has largely ceased and stellar evolution proceeds quietly as the existing stars age and evolve. What makes the future of the Milky Way particularly poignant from a human perspective is that it coincides with the future evolution of our Sun. In about 5 billion years, roughly when the merger with Andromeda will be underway, our Sun will exhaust the hydrogen in its core and begin to expand into a red giant. This phase will likely engulf the inner planets, including Earth, ending the story of life on our planet as we know it. By the time the merger is complete and Milky Way has formed, our Sun will have shed its outer layers and contracted to a white dwarf, a dense, cooling ember of its former self. It will be just one of billions of such stellar remnants in the newly formed elliptical galaxy, its planets either destroyed during the red giant phase or left orbiting as cold, dead worlds around the fading white dwarf. This parallel between the life cycles of our Sun and our galaxy reminds us of the multiple timescales at work in the cosmos. Humans live for decades, civilizations for centuries or millennia, species for millions of years. Stars like our Sun live for billions of years, while galaxies evolve over tens of billions of years. Each scale has its own rhythm and pattern, its own story of birth, maturation, and eventual transformation. Yet these disparate timescales are connected. The elements formed in ancient stars billions of years ago became the raw materials for our solar system, our planet, and ultimately ourselves. The ongoing evolution of the Milky Way provides the context in which our solar system exists, and life on Earth has flourished. And the future fate of our galaxy sets the stage for whatever comes next in the grand cosmic drama. For now, we live in a relatively quiet period in our galaxy's history. Star formation continues at a modest rate. The spiral structure, while constantly evolving, maintains its overall pattern. Our Sun orbits steadily through the galactic disk, carrying Earth and the other planets with it. This period of relative stability has allowed life to develop and thrive on our planet for billions of years. But change is coming, as it always does in the cosmos. The Milky Way's future holds both gradual evolution and dramatic transformation. The steady consumption of its gas supply will slowly reduce the rate of star formation. The impending collision with Andromeda will reshape the galaxy's structure and accelerate its transition to a quiescent elliptical. The relentless expansion of the universe will gradually isolate our local group from the rest of the cosmos. These changes, while too slow to affect human civilization directly, remind us that even the most seemingly permanent cosmic structures are impermanent on the longest timescales. Galaxies, like stars and planets and people, have life cycles. They are born, they change and evolve, and eventually they transform into something quite different from what they began as. The story of the Milky Way, spanning from its birth in the early universe to its distant future as part of a merged elliptical galaxy and beyond, is a story of constant change and evolution. It is a reminder of the dynamic nature of the cosmos, where nothing, not even a galaxy containing hundreds of billions of stars, remains the same forever. Yet within this constant change, there are patterns and cycles that give the universe a kind of order and rhythm. The cycle of star formation and stellar death that enriches galaxies with heavy elements. The hierarchical assembly of cosmic structure through mergers and accretion. The gradual transition of galaxies from active youth to quiescent old age. These patterns, playing out across billions and trillions of years, form the grand narrative of cosmic evolution. As humans, with our brief lives and even briefer recorded history, we glimpse only a moment in this vast cosmic story. Yet through observation, analysis, and theoretical modeling, we have been able to reconstruct much of our galaxy's past and project its likely future. This achievement stands as a testament to human curiosity and ingenuity, to our ability to understand processes that unfold over timescales far beyond our direct experience. In contemplating the future of the Milky Way, we are reminded of our place in the cosmic context. We exist in a particular moment in our galaxy's long history, when conditions happen to be suitable for life as we know it. Before us stretches a future that we will not witness, but can nonetheless understand and predict. Behind us lies a past that we did not experience, but have pieced together through careful study of the clues left in our galactic surroundings. This perspective both humbles us and expands our horizons. We are transient beings in a galaxy that itself is changing and evolving over vast spans of time. Yet through our minds and our science, we can comprehend this broader context, connecting our brief moment of existence to the grand sweep of cosmic history and future. The Milky Way, like all things, is changing, and someday it too will fade. As our journey through the cosmic history of the Milky Way comes to a close, we find ourselves back where we began, gazing up at the misty band of light that stretches across our night sky. This pale river of stars, this galaxy we call home, has been our companion throughout human existence. Yet only recently have we begun to understand its true nature, its history, and its destiny. We have traveled together across vast spans of time, from the primordial darkness before the first stars ignited, through the turbulent youth of our galaxy's formation, to the majestic spiral we see today, and onward to the distant future when the Milky Way will merge with Andromeda and gradually fade into quiescence. In this journey across 13 billion years, we have witnessed the birth and death of countless stars, the slow accretion of galactic structure, and the delicate balance of forces that shapes our cosmic home. The story of the Milky Way is, in many ways, the story of the universe itself. Within our galaxy, the fundamental processes that govern cosmic evolution have played out countless times. The gravitational collapse of gas clouds into stars, the nuclear fusion that powers stellar furnaces and creates heavy elements, the explosive deaths of massive stars that scatter these elements into space, the gravitational dance of stars and gas and dark matter that creates structure on all scales. All of these processes, central to the evolution of the cosmos as a whole, are written in the history of our galaxy. But the Milky Way's story is also our story. Every atom in our bodies heavier than hydrogen, helium, and trace amounts of lithium was created in a star, many of them within our galaxy. The carbon in our cells, the oxygen we breathe, the calcium in our bones, the iron in our blood, all were forged in stellar furnaces that lived and died before our sun was born. We are, quite literally, made of star stuff. Our physical substance connected directly to the galactic processes we have explored. This connection goes beyond the merely physical. The conditions that allowed life to emerge on Earth, from the formation of heavy elements to the stable environment provided by our sun's orbit in the galactic habitable zone, were established by the Milky Way's evolution. Our very existence is intimately tied to the specific history of our galaxy, its rate of star formation, its merger history, its spiral structure, and countless other factors that created the conditions for life to arise here. Throughout human history, the Milky Way has been a constant presence in our night sky, inspiring wonder, mythology, and eventually scientific inquiry. Ancient cultures around the world incorporated this celestial river into their cosmologies and stories. The Chinese called it the Silver River. To the Norse, it was the path to Valhalla. The Aborigines of Australia saw it as a river carrying a giant fish with the minor stars as fish scales. The Maya saw it as the road to the underworld. Across continents and millennia, humans looked up at the same misty band and wove it into their understanding of the cosmos. It was only in the early 17th century, when Galileo first turned his primitive telescope toward the heavens, that we began to understand the true nature of this celestial river. What appeared to the naked eye as a continuous band of light resolved into countless individual stars, too distant and faint to be seen separately without optical aid. This discovery was the first step in a scientific journey that continues to this day, as astronomers use increasingly sophisticated instruments to probe the structure, composition, and history of our galactic home. The Milky Way has revealed itself to us gradually, like a landscape emerging from morning mist as the sun rises. With each technological advancement, from Galileo's simple telescope to modern radio interferometers and space observatories, we have seen our galaxy with greater clarity and detail. We have mapped its spiral arms, discovered its central black hole, traced its halo of ancient stars, and detected the invisible dark matter that provides the gravitational scaffold for the entire structure. Yet, for all our advances in understanding, there remains something profoundly moving about the simple act of looking up at a dark sky, far from city lights, and seeing the band of the Milky Way stretching overhead. In that moment, we connect not only with the scientific understanding we have gained, but with the human experience across time, with all those who have looked up in wonder at the same celestial spectacle. As we stand beneath the stars, we occupy a unique place in cosmic history, able to comprehend the story of our galaxy in ways that were impossible for most of human existence. We now know that the Milky Way began as a small collection of gas and dark matter in the early universe, one of countless similar structures forming throughout the cosmos. We understand that it grew through both the accretion of gas from the cosmic web and through mergers with smaller galaxies, gradually assembling the majestic spiral we inhabit today. We can trace the lives and deaths of stars within our galaxy, from the massive short-lived giants that explode as supernovae to the small, dim red dwarfs that burn slowly and steadily for tens of billions of years. We understand the cycle of stellar birth and death that has gradually enriched our galaxy with elements heavier than hydrogen and helium, making possible the formation of rocky planets like Earth and eventually of life itself. We have mapped the distribution of gas throughout the Milky Way, from the dense molecular clouds where new stars are born to the hot, tenuous plasma that fills much of the volume between stars. We have discovered that this gas is not evenly distributed, but concentrated in the spiral arms, where it is compressed by density waves moving through the galactic disk, triggering the formation of new stars. We have explored the galactic center, hidden from our direct view by thick clouds of dust, but revealed by radio, infrared, and X-ray observations. There, we have found a dense cluster of stars orbiting around a supermassive black hole, Sagittarius A star, with a mass of about 4 million suns. We have watched as stars complete their orbits around this invisible gravitational sink, moving at speeds of thousands of kilometers per second as they swing past the black hole at their closest approach. We have detected the dark matter halo that surrounds the visible Milky Way, extending far beyond the stellar disk and contributing the majority of our galaxy's mass. Though we cannot see this component directly, we infer its presence from its gravitational effects on the stars and gas we can observe. The nature of this dark matter remains one of the great unsolved mysteries in physics, but its role in shaping the formation and evolution of our galaxy is beyond doubt. We've identified the satellite galaxies that orbit the Milky Way, from the relatively large Magellanic Clouds to tiny dwarf spheroidals containing just a few 100,000 stars. We have discovered streams of stars wrapping around our galaxy, the remains of smaller galaxies that have been torn apart by the Milky Way's tidal forces. Through these observations, we have pieced together our galaxy's history of mergers and accretions, the process of galactic cannibalism that has contributed to its growth over cosmic time. We have located our own solar system within this vast cosmic structure, about 27,000 light-years from the galactic center, in a minor spiral feature called the Orion Arm. We have measured our motion around the galactic center, completing one orbit every 230 million years, and our oscillation up and down through the galactic plane, crossing the midplane approximately every 30 million years. And we have projected the future evolution of our galaxy, from the gradual decline in star formation as its gas supply is depleted, to the dramatic merger with Andromeda that will begin in about 4.5 billion years. We have modeled the transformation of the Milky Way from a star-forming spiral to part of a larger, quiescent elliptical galaxy, and even speculated about its ultimate fate in the extremely distant future, as the stars die out and the galaxy fades. All of this knowledge, accumulated through centuries of observation and analysis, gives us a perspective on our cosmic home that no previous generation of humans has possessed. We see the Milky Way not as a fixed, eternal feature of the heavens, but as a dynamic, evolving system with a beginning, a middle, and an eventual end. We understand our place within this system, not as privileged observers at the center of creation, but as inhabitants of one small planet orbiting one ordinary star in the galactic suburbs. This perspective both humbles us and expands our horizons. We are tiny beings on a tiny world, one of billions of planets in one of hundreds of billions of galaxies in the observable universe. Yet through our intelligence and our science, we have been able to comprehend structures and processes far beyond the scale of our direct experience. We can hold in our minds the concept of a galaxy spanning 100,000 light-years, even though the distance light travels in a year is already almost beyond our intuitive grasp. The story of the Milky Way also connects us to the deepest questions of origins and destiny. Where did we come from? Where are we going? The scientific answers to these questions involve the birth of stars from interstellar gas clouds, the formation of planets around young stars, the emergence of life on at least one of those planets, and the eventual fate of both our species and our cosmic home. The Milky Way provides the context for this entire narrative, the stage upon which the drama of life unfolds. As we go about our daily lives on this small blue planet, the Milky Way surrounds us, unseen during daylight hours but always present. Each night, when darkness falls and the stars emerge, we have the opportunity to look up and see our galaxy from the inside, to recognize that we are not separate from this cosmic structure, but an integral part of it. The boundary between us and the galaxy is an illusion. We exist within the Milky Way, composed of material processed through its stars, our fate tied to its evolution. In this recognition lies a profound sense of connection, a cosmic perspective that transcends the artificial divisions of human society. Seen in the context of our galaxy's vast scale and ancient history, the differences that seem so important in our daily lives fade into insignificance. We are all galactic citizens, our ultimate heritage written not in the borders of nations or the distinctions of cultures, but in the stars that surround us and the elements they have created. This cosmic perspective can also inform our relationship with our home planet. Earth is a tiny oasis of life in the vastness of space, the only world we know where life has emerged and evolved over billions of years. From the perspective of our galaxy, with its hundreds of billions of stars and likely trillions of planets, Earth is extraordinarily rare and precious. The narrow boundary of atmosphere that separates us from the vacuum of space, the delicate balance of conditions that makes life possible, these appear all the more valuable when seen against the backdrop of cosmic scales. As we face challenges like climate change, resource depletion, and loss of biodiversity, the galactic perspective reminds us of the uniqueness and fragility of our planetary home. It encourages us to take the long view, to consider not just immediate benefits, but the sustainability of human civilization over generations and centuries. Just as the Milky Way has evolved over billions of years, Earth's biosphere has developed over similar timescales, creating the conditions in which humanity could emerge and thrive. The study of our galaxy also prompts questions about our possible cosmic companions. With hundreds of billions of stars in the Milky Way, many of them hosting planets, it seems likely that Earth is not the only world where life has emerged. Recent astronomical discoveries have revealed thousands of exoplanets, some of them similar in size and orbit to Earth, potentially capable of supporting liquid water on their surfaces. While we have not yet detected signs of life beyond Earth, the sheer numbers suggest that it may exist elsewhere in our galaxy. If other intelligent species have evolved in the Milky Way, they too would gaze up at the spiral arms illuminated with the light of billions of stars. They too might wonder about their place in the cosmic order, developing their own mythologies and eventually their own sciences to understand the galactic structure they inhabit. Perhaps they too have reached a stage where they can comprehend the history and future of our shared galactic home, looking outward from their own world just as we look outward from ours. The possibility of other civilizations in our galaxy raises profound questions about humanity's future. Will we ever develop the technology to travel between stars, to explore directly the wonders we now observe only from a distance? Will we ever make contact with other intelligent species, if they exist? Or are we destined to remain confined to our solar system, or even just to Earth, limited by the vast distances that separate stars even in our local galactic neighborhood? The history of the Milky Way spans nearly the entire age of the universe, from the formation of the first stars and protogalaxies less than 1 billion years after the Big Bang, to the present day, nearly 14 billion years later. During most of this vast time span, there were no humans to observe and appreciate the galaxy's majestic structure. Our species has existed for just a few 100,000 years, less than 100,000th of the Milky Way's lifetime. Written human history extends back only a few thousand years, an even smaller fraction of the galactic timescale. Yet in our brief existence, we have achieved something remarkable. We have reconstructed much of the history of our galaxy, from its earliest origins to its current state, and projected its likely future evolution. Through observation, analysis, and theoretical modeling, we have created a narrative that spans timescales far beyond human experience. This achievement stands as a testament to the power of human curiosity and intelligence, our ability to comprehend processes that unfold over billions of years. In the context of the Milky Way's long history, human civilization is just beginning. If our species survives and continues to develop, what might we achieve in the next 1,000 years, or million years, or billion years? Might we expand beyond Earth to other planets in our solar system, and eventually to other star systems within our galaxy? Might we develop technologies that allow us to harness energy on scales currently unimaginable, or to manipulate matter in ways that seem like science fiction today? The future of humanity within the Milky Way is a story yet to be written, a potential limited only by the laws of physics and our own ingenuity. Even as we contemplate these possibilities for the future, we remain grounded in the present, inhabitants of one small planet orbiting one ordinary star. The Milky Way, we observe today, is a snapshot of an ongoing process of evolution, a single frame in a cosmic movie that began billions of years ago and will continue long after our time. The stars we see are not eternal but temporary phenomena, each with its own lifespan and destiny. Some are young, recently formed from collapsing gas clouds. Others are middle-aged like our Sun, steadily converting hydrogen to helium in their cores. Still others are nearing the ends of their lives, expanding into red giants or preparing to explode as supernova. This ongoing cycle of stellar birth, life, and death is central to the story of the Milky Way. It is the process that drives the galaxy's chemical evolution, gradually increasing the abundance of elements heavier than hydrogen and helium. It is the source of the energy that makes the galaxy visible, the nuclear fusion reactions in stellar cores that produce the light by which we see the Milky Way and all other galaxies. And it is the ultimate origin of the elements that make up Earth and all living things, including us. When we look up at the band of light that is the Milky Way stretching across the night sky, we are seeing starlight that has traveled for decades, centuries, millennia, or even tens of thousands of years to reach our eyes. Some of the stars we observe may have already died, their light still traveling through space long after the star itself has exploded as a supernova or faded into a white dwarf. What we see is not the Milky Way as it is now, but as it was when the light left each star, a palimpsest of different times layered together by the finite speed of light. This aspect of our observation of the Milky Way mirrors our understanding of its history. We do not observe the galaxy's past directly, but reconstruct it from the clues left in the present. The oldest stars in the halo preserve a record of conditions in the early universe. The streams of stars wrapping around the galaxy trace past merger events. The chemical composition of stars of different ages reveals the progressive enrichment of the interstellar medium. From these and many other lines of evidence, astronomers have pieced together the narrative of our galaxy's formation and evolution. The Milky Way we inhabit today is the product of nearly 14 billion years of cosmic evolution, a structure that emerged gradually from the almost uniform conditions of the early universe. It began as a small overdensity in the primordial matter distribution, a seed that grew through the relentless pull of gravity. It accreted gas from its surroundings and merged with other proto-galaxies, gradually building up its mass and complexity. It formed generations of stars that lived and died, each contributing to the enrichment of the interstellar medium with heavy elements. It developed the rotating disk, the spiral arms, the central bulge, and all the other features that define its current structure. This evolution continues today as the Milky Way forms new stars, accretes gas from the intergalactic medium, and gradually merges with its satellite galaxies. It will continue into the future as star formation slowly declines, as the merger with Andromeda transforms our galaxy into a giant elliptical, and as the stars gradually die out, leaving a collection of stellar remnants orbiting in the dark. The Milky Way has a lifespan far longer than any human timescale, but it too is impermanent on the grandest cosmic scales. As we contemplate this vast sweep of time, from the birth of the first stars to the distant future when the last stars fade away, we are reminded of our own transience. Human lives are brief, human history is short. Even the likely lifespan of our species is limited compared to the age of our galaxy. Yet, in our brief moment, we have achieved something remarkable. We have understood something of the nature and history of the vast cosmic structure we inhabit. We have placed ourselves in context, recognizing that we are not separate from the Milky Way, but an integral part of it, our very substance forged in its stars. This understanding can inform our relationship with the cosmos and with each other. It can inspire a sense of wonder at the beauty and complexity of our galaxy, and a sense of kinship with all other inhabitants of Earth, with whom we share both a planetary home and a galactic context. It can encourage us to take the long view of our species' future, to consider not just immediate concerns, but the potential for humanity to exist and thrive for thousands or millions of generations to come, continuing to explore and understand the Milky Way that is our cosmic home. The perspective gained from studying the Milky Way can also remind us of the value of curiosity, exploration, and the pursuit of knowledge for its own sake. The discoveries that have revealed the structure and history of our galaxy were not driven by practical applications or immediate benefits. They arose from the fundamental human desire to understand the world around us, to make sense of our place in the cosmos. This pure curiosity has led to some of humanity's greatest intellectual achievements, including our modern understanding of the Milky Way. As we look to the future, both of our species and of our galaxy, we can anticipate further discoveries that will deepen and perhaps transform our understanding. New telescopes and observation techniques will reveal aspects of the Milky Way that remain hidden from us today. Advanced computer simulations will model galactic evolution with increasing sophistication and detail. Theoretical breakthroughs may solve long-standing puzzles, such as the nature of dark matter or the physics of galactic centers. These future discoveries will build on the foundation laid by generations of astronomers, from Galileo pointing his telescope at the Milky Way to contemporary researchers analyzing data from space observatories and radio interferometers. Each observation, each analysis, each theoretical insight has contributed to our current understanding, a collective achievement spanning centuries of human effort. And this understanding, impressive as it is, remains incomplete. A work in progress that future generations will continue to refine and extend. In this ongoing quest to understand our galactic home, we find a mirror for the broader human enterprise of science and discovery. Each generation builds on the work of those who came before, gradually expanding the sphere of human knowledge. Each breakthrough, each new observation, opens up further questions to explore. The horizon of the unknown recedes as our understanding advances, but it never disappears entirely. There is always more to learn, more to discover, more to understand about the Milky Way and our place within it. This perspective on the growth of knowledge, seeing it as a cumulative, multi-generational project, can also inform how we think about humanity's future. Just as our current understanding of the Milky Way builds on centuries of previous work, the achievements of future generations will build on the foundation we lay today. The choices we make now, from how we manage Earth's resources, to how we invest in science and education, to how we organize human society, will shape the options available to those who come after us. In the context of the Milky Way's long history, and even longer future, human civilization is in its infancy. If we navigate the challenges of the coming centuries successfully, maintaining a habitable planet and developing sustainable ways of living, our descendants may witness developments in the ongoing story of our galaxy that we can scarcely imagine. They may develop technologies that allow them to explore directly what we can now only observe from a distance. They may answer questions about the Milky Way that we have not yet even thought to ask. This potential future for humanity within our galaxy depends not just on technological development, but on wisdom, on using our understanding of the cosmos to inform how we live in the present. The perspective gained from studying the Milky Way, seeing ourselves as part of a vast and ancient cosmic structure, can contribute to this wisdom. It reminds us of both our smallness in the cosmic context and our remarkable ability to comprehend structures and processes far beyond our physical scale. As our journey through the cosmic history of the Milky Way concludes, we return to the present moment, to our place within this magnificent spiral galaxy. We are made of its substance, forged in its stars. We observe it from the inside, comprehending its structure and evolution through careful study and analysis. We exist in a particular moment in its long history, when conditions happen to be suitable for life as we know it, and we look toward its future, which will unfold long after our brief lives have ended. In contemplating the birth, evolution, and eventual fate of our galactic home, we gain a deeper appreciation for our own place in the cosmic order. We are not separate from the processes that have shaped the Milky Way, but an integral part of them. The same physics that governs the formation of stars and the motion of gas clouds also governs the atoms in our bodies. The same history of stellar nucleosynthesis that enriched our galaxy with heavy elements also provided the raw materials from which Earth and all living things are made. This connection to the larger cosmos, this recognition that we are not merely observers of the Milky Way, but participants in its ongoing story, offers a perspective that transcends our daily concerns. It invites us to see ourselves as part of something larger and more enduring than individual human lives, or even human civilization as a whole. It encourages us to consider our responsibilities, not just to each other and to future generations of humans, but to the broader web of life on Earth and perhaps eventually to life elsewhere in our galaxy. The Milky Way was not always here. In the beginning, there was only the potential for structure, quantum fluctuations in an otherwise smooth cosmos. Through billions of years of evolution, guided by the fundamental laws of physics, our galaxy emerged from this potential, growing and changing, developing the complex structure we see today. And it will not always be as it is now. In the fullness of time, it will merge with Andromeda, transform into an elliptical galaxy, and eventually fade as its stars die and no new ones are born to replace them. But for now, in this moment, it shines. A spiral of stars, carrying us through the dark. Sleep now, beneath its arms, and dream of the long spiral home